Good morning. Okay, now I don't need to yell anymore because I have a microphone. Today's session is the last session and it is about the future. And since about half of the audience are PhD students, then I think that it is for you, because you will be the people who will be on top of science in 10 to 20 years. Our first presenter is Giovanna Tinetti, who will talk about the Ariel space mission and, well, exoplanets characterization. Thank you.
Tere, thank you so much, Anna, for this presentation, but also thanks for the organizing committee for giving me the opportunity to speak at this extremely interesting workshop and conference. So before we get to the future, I would like just to ponder a few seconds on the present, because it tells us a lot about the history of this relatively young field. 30 years ago, or a little bit more than that, we didn't know the exoplanet existed. And all of a sudden, we have to face, as a community, more than 6,000 exoplanets now, a number that is increasing by the day. And it's not just the number that is important. I think what is useful to see in this graphic, showing one of the most recent exoplanet demographics, and in particular, what kind of technique is delivering what. As you can see, the parameter space is covered by different technique in a different way. And the first message I'm receiving out of the competition, they're all useful because they're all probing different parameter space for the star, for the planet, for the orbit. So we need everything. And it's true that so far, in a certain sense, the big cheeses in terms of techniques have been mainly transit and radio velocity. I think what is this graph is also telling us is that we are missing a lot of information in this part. And we're missing information, in particular, larger distance from the star. Most of the planets that have been discovered so far are biased towards planets that are very close to the star. It's a bias that comes mainly from the technique of transit and radio velocity. And although these have been fantastic, we really need to understand a little bit better what's happening here. And this is important also because, as we heard yesterday about planet formation theories, we need to have the demographics also larger distance, because otherwise there isn't a proper constraint for people who are doing planet formation modeling. Now, the good news is that we have a suite of space missions that are currently operating, but for which we are waiting the new release of data. I'm talking about Gaia here. The expectation is that the new release of data should open up really the discovery of thousands and thousands of new planets with astrometry, new technique, new quoted in terms of delivery of more planets. But then, basically, we have PLATO and Roman also launching in the next couple of years, and Earth 2.0 as well. Now, PLATO and Earth 2.0 will deliver more planets through transit, but they are both next generation of missions, and so they will really push for very small planets and larger distance even through transit. So again, they will clearly cover part of this parameter space. And when it comes to Roman and Earth 2.0, they'll look also at macrolensing. And so the hope is that this sort of figure will change dramatically in the next 5 to 10 years. And I think we need to expect that to happen, which is great. Simultaneously, I love the talk of Diego yesterday, because he spent quite a bit of time to explain why it's super important to start connecting this even more than we did in the past, the solar system with the information that's coming out of disks, and in particular all the incredible images and spectra out of ALMA, but also out of direct imaging of disks. And also this is expecting to evolve, because not only ALMA will operate and not only direct imaging from the ground with a number of facilities, more and more will come out of the solar system, but also there is SKA that will probably deliver more information about objects that are at the level of pebble in terms of size, so clearly putting extra constraints in the formation model, but also the E-ELT, of course, and direct imaging. And so to me, also, this is going to be quite revolutionized in the next 5 to 10 years. Now, after this, I want to really focus a little bit more on atmospheres. And I just wanted to say that most of you in the audience nowadays are giving for granted that we're doing atmospheric composition. But it wasn't certainly the case when I started in this field many years ago, in the early 2000s. In the early 2000s, doing atmospheric composition was almost science fiction. We were all thinking in order to do that, we had to do immediately very big and large and ambitious telescope like TPF, Darwin, and the sorts. And so it was only with transit, in a certain sense, that we started to understand that you can do things with different techniques. And what I'm really pleased to say nowadays is that, one, not only is no longer a science fiction technique, we really have great data for atmospheric composition, but like for the detection techniques, we have now a number of techniques that are delivering not only great results, but they're, again, like the detection technique, they're all very complementary. So it's not about one being better than the other. It's about moment of time. At the moment, we have a lot of transiting data, so of course it would be silly not to take advantage of the transit technique. That is also one technique that we started first, and so we know almost better. We know better also the limitation of it. But at the same time, it's super important to push even further direct imaging that is delivering fantastic data. The planets that we're looking with these two, let's say, classes of techniques, it's not just one or two, are really very different. Direct imaging planets are typically very far away from the star. Transiting are looking at planets that probably migrated in when it comes to giant planets. And so, again, we need both. It's not about one or the other. And the question is more when and how. But we shouldn't forget at all the complementarity and synergy from the ground. And I'm not going to spend more time about the ground in my talk, simply because there are two talks later on today that will really look into this at a high level of precision. But I really want to make my point that ground and space are synergistic and complementary. We really need both, because there are things that we can do quite well from space. For instance, broad wavelength range, having a spectrum in one shot, going to the infrared or regions that you can not do very easily from the ground. But from the ground, you can get resolutions that are science fiction from space. And so you really need both, and you need to have both working in synergistically. Now, talking about the present, Webb has quite revolutionized the way we are doing spectroscopy about exoplanet atmospheres. And to me, the spectrum says more than many words. This is a direct imaging spectrum, and the level of sophistication of the spectrum for most of us that were used to Herobars and broadbands until very recently is just mind-blowing. When it comes to transit, I will focus a little bit more on transit from now on, simply because it's, as I said, the technique at the moment for which we know more information and for which we have more planets also to select from for our sample. Now, I think Webb data are really transformational, whether it is transit or eclipse or phase curves. The quality of the data compared to the past is just a different thing. And this means that I think what we need to do is to really step up in terms of modeling, because I think what Webb is screaming at us is that the data are so much better than our model and our way to interpret spectra. And it shouldn't be a surprise, because we have been training with much poorer quality data so far with Hubble, Spitzer, and other facilities. And so clearly here we're stepping up in terms of wavelength range being probed and also in terms of signal to noise. And all of a sudden, our models, talking about retrievals, but also other atmospheric type of models, are not as good as we need. And so I'm trying to make my case here with a couple of examples that comes from the work of my team. By any means, we are not the only one that we're exploring the data web, not at all. It's clearly an effort of the entire community. But what in particular we have been trying to do with my team at KCL is to look at potential different interpretation of some of the data that have been published, and trying to see whether some of the current assumptions are can be challenged. And this is not challenging for the sake of challenging, it's more to see how far we can go in understanding what is the degeneracy in the data. And so are we really getting the most out of this data, or we are assuming things for the moment just because we're the first thing that we assumed that perhaps should be revisited. And clearly there is an enormous amount of work that needs to be done, and I hope that the new generation will really pick up on this, because it's really something important. So for instance, in the case of WAS 39b, we tried to use a number of hierarchical retrievals, but also ab initio models, going back and forth between the two, to try to understand, for instance, whether there is a scenario for which you can explain the data using more silicate-based kind of chemistry as opposed to sulfur-based. We are not trying to say that sulfur is not there. We are trying to say, okay, there is more to the picture. And given that this particular planet seems to have some clouds, there is a lot of complexity connecting to that, and also degeneracy, in part because many of the optical properties of clouds and hazes are not known. And so all of a sudden you see where the problem is. But also line lists are not always to the level that we need to interpret this data. And although spectroscopists are really helping, there is still a lot of work to be done. Clearly, things are even more visible when it comes to planets that are in the regime of super-Earths, and K218b doesn't need any presentation, is probably one of the most studied planets, iconic planet in the field. And clearly, there have been many papers out, even looking at potential biosignature for this particular planet. What we did was mainly to try to see where we could reconcile basically the data at shorter wavelength, taking NIRSPEC and NIRIS, and a longer wavelength with MIRI, putting them together. Because when you try to analyze them separately, as has been done before this paper, the amount of degeneracy is huge. You can fit so many different type of scenarios that is very hard. With the exception of a few molecules are clearly there, it's very hard to get a big picture. And again, to make the point in this conference where we're talking about the importance of star, what we have pointed out is that for the star, K218, not even the mass and the radius are so well known. And if you start to play with these basic parameters, also the retrieval will give you different abundances, unsurprisingly. Also, many of the models that have been done in the past in photochemistry have used stars that are not specifically K218, which means that, again, you're introducing potentially some errors. What I'm trying to say here is that when you get to this level of complexity, you really need everything. You need the star to be really well known, because then you're perturbing all your uncertainty in the planet, and so on and so forth. And something that we have proposed to reconcile the various data sets is the presence of some hazes, similar to the one that you have on Titan, which is potentially not unsurprising on a planet like this that is close to, relatively close to an M dwarf. If you include some hazes, then you can reconcile well, basically, the data at the shorter wavelengths and the longer wavelengths. So otherwise, it's very hard to put them both, because this data seems to be much more transparent. You have a much higher scale height that we're seeing compared to the data on the left. So this is, again, just two examples to say that there is more to be done by the entire community for all the data set of Webb, and there are many more out. Now, I'm sure that in the audience I don't have to convince you that the star is important. But somehow it's interesting to see how there was an historical evolution of how planets and exoplanets lived together for a while. At the beginning, in particular for those like me or old enough to remember the very first measurements of atmospheres, there was a lot of skepticism in the field that we could extract a signal of an exoplanet atmosphere because of the stellar activity. Back then, we certainly made a bit of a case in suggesting that, yes, of course, star is important, but if you go to the infrared, perhaps we have an opportunity to see through and to have some mitigation sort of a technique in order to get the signal out. And also, not all stars are very active, and so on and so forth. But then somehow, given the success of the field of exoplanet atmospheres, we almost forgotten a little bit about the importance of the star. And now Webb in particular is reminding us that the star is there. And specifically, if you focus in on small planets and a small planet around a relatively active star, and M dwarfs most of the time are, then the star is really there. And all of a sudden, you might not know in certain cases whether it's the planet, the planetary signal, or is the star. So I'm not saying this in a negative way, but we really need to step up again in our preparation, because we can't really forget about the star and then as an afterthought say, oh, there is also the star. And this is a message also that is coming out of Hubble data. This is a study that we did with my team at the UCL and KCO. And what you're looking at here is a population study done with Webb, pushing together STIS data and WSC3. And, well, we started thinking that we would do a population study about clouds, and surprise, surprise, we did a population study about stellar activity, because it turns out that many of the stars were showing in the UV something that we didn't see at all in the near infrared. Yeah, quite a lot of discrepancy from different visits. Now, if you don't correct for that activity, you end up, for instance, getting abundances of water vapor and temperature. We focus on this particular study on very simple parameters for the atmosphere that are wrong. So you really need to correct for those. So again, another lesson learned from Hubble and from the current data. And again, there were already a lot of talks in the first day reminding us about flaring activities, and if you have flares, then the situation is even more dramatic. Again, there are data that are coming out of X-rays that are telling us more and more about the amplitude and also frequency of stellar flares, but also data from TESS, for instance, and other facilities that are doing that in the visible. I'm not going to talk about MOV because I think Fatime already talked about it on the first day, but this is just to say that I'm quite excited about the launch of this small satellite which is the first satellite launched by Blue Sky Space, which is a company that I'm co-founder and co-director. We're launching in November on Transport 15, and although we're talking about a 16-unit CubeSat, so this is definitely not Hubble, the fact that we can look at many targets through time and monitor them through time, then it means that we can really see, for instance, if there is some flaring activity, we should be able to see basically the impact, in particular in the UV, something at the moment we don't necessarily have, because Hubble, great, but you will get one snapshot in time and not the ability really to monitor things through time. Okay, so this brings me to this overview of many of the facilities that are currently operating and the ones that are about to be launched or to be in operation. And this is to say that we really need all of these facilities for the many reasons that I tried to touch upon in these previous slides. And even more importantly, we need the ground and space really to go together, because exoplanets and stars and disks are really complex objects. And so we need all of this in order to understand what's going on. Now, let me perhaps spend a few minutes to talk about Ariel, because I know that I was supposed to talk about Ariel. And it's not that I don't want to talk about it, but I just want to make sure that we all have in mind that Ariel is coming into a situation that I think is in great evolution for exoplanets and stars and disks, and we need to make sure that the program of Ariel is really well anchored to what is happening with all these other facilities, because otherwise we would waste the time of this incredible mission. So Ariel will be launched at the end of this decade. We are talking about a 1-meter class telescope will be launched in L2. And perhaps the unique selling point compared to other facility is the ability to do in one shot 0.5 to 7.8 micron in the infrared. And this is important for a number of reasons. Removing stellar contamination as much as you can. Of course, we don't have the UV, but is as far as you can go, a short wavelength when you have an infrared mission. But also the ability to be very agile and very efficient, because we want to aim at the big population study. We want to be able to probe about 1,000 exoplanets in the first 4 years of the mission, and hopefully, there is no showstopper to keep going. And the other difference, perhaps, with other facilities that might be in certain region even more performing an aerial, but the fact that we can plan the entire survey as one big experiment and try to map the parameter space of stars and planetary parameter as much as possible. The entire idea of aerial is really to try to give the big picture, and then to use that to anchor all the other facilities that are operating simultaneously or after aerial. If you want to know more about the mission, about the many initiatives, you can go to this link tree, aerial telescope, and you have the link to all our initiatives. So if I don't have time to speak about some of these initiatives, then you can find it there. But just a few words about the spacecraft and the payload. The payload is basically designed and delivered by a consortium of 16 ESA countries, and we have a contribution from NASA, JAXA, and CSA. We are in full swing with the test campaign. All the bits and pieces and the subsystem are literally this week coming to RAL, and there is a number of tests that are planned in early November. So this is happening now, so a lot of excitement from the engineering side. The idea is that when the test campaign, that of course will last some time, will be ready, and when the payload is ready, then it will be delivered to Airbus to be assembled with the spacecraft before launch. Behind aerial, both the payload but also the science are more than 600 scientists and engineers right now. This is one of the recent pictures that we took in one of the consortium meetings. And as I made as a point also in our talks, we're calling an aerial mission as opposed to a telescope, because when you have all these people working together for more than 10 years, it sounds like really a mission. Our goal is really to deliver the best possible science and instrument, and it's a great path, because you're really bonding with many different ways of working and culture and in areas of science and engineering. As I tried to mention before getting into aerial, there is a lot that we're getting out of Webb. Webb is a fantastic test bed for understanding from real data what is possible and what, on the contrary, is more of a dream. And so for the moment, we're working on looking at complementarity and synergies in the case Webb and aerial are flying together. And it's definitely possible, because it looks like Webb can continue for a while, which would be fantastic. And they are very complementary objects. So, for instance, something that we are definitely planning even more to do with aerial at this point is to use the fact that it's a dedicated mission, so we can do time domain, we can keep observing, for instance, some of benchmark targets through time, and look at the variability both of the planetary atmosphere and the star. And to do that, you can use a few tens of objects really to anchor a lot of the other observations. But we can also do many more phase curves, so following the planet throughout the orbit as opposed to just stopping on transit and eclipses. Planets are 4D complex objects, they change in time and space, and so let's use the time in our hands really to do this kind of experiment. And so for the moment, we are trying to modify our plan to include more planets for which we want to do phase curves, because we believe that the information content in terms of science is so much higher that it really deserves more time. And clearly, Webb will have difficulty in dedicating so much time for phase curve of time domain for so many objects. I would love to see that, but I can understand that other fields in astrophysics might want also Webb time. Aerial will also be probably very strong in looking at population behavior. That's why, in a certain sense, we are proposing Aerial in the first place. So looking at searching for chemical trends, cloud transitions, Now, what you're looking at here are some simulations that we produced back in 2020 for the adoption. There are many more, much more sophisticated large-scale simulation that the consortium is putting together for publication, basically trying to do really end-to-end simulation from some of the models of planet formation up to what it was being observed with aerial and what we can extract out of the data. And this will be done by many teams in parallel because we want to make sure that what we are extracting is as good as possible. But still, these are simulations, so it doesn't mean that then in the reality things are so easy. So that's why in parallel we really need to use the current data to learn even more. And just to follow up a little bit on what Diego said yesterday, clearly the message from the community of disks and planet formation and the need to look at more element ratios, we really need to look whether this is possible or not in the data. And again, we have many simulations looking into this possibility with aerial. Again, results promising. We're talking about simulations, so hopefully it will be the case also with real data. I have very little time available, so I'm sorry for that. So I will just say a couple of things before I go to the final slide. One, if you're interested about the target candidate for aerial, these are kept in a repository on GitHub, so everybody can have a look at this. You can see what are the targets that are being considered, what the one for which we need your help for mass characterization, and so on and so forth. I hope that Camilla has convinced you that her aerial stellar catalog is absolutely wonderful. She and the team for stellar characterization in aerial have done a massive work really to make sure that the stars are well characterized well before aerial is launched, so we don't end up with problems when it's there. And there is also a test campaign that is going forward, led by Sudeshna Borosakia with Hubble about activity. Lots of work about databases for spectroscopy, cloud optical properties, and chemistry. Data challenges, and since I don't have time to talk about all this, I will just come to my very last slide. Sorry, Tina and Anna, which is the Aerial Open Conference. So if you want to know more, and clearly I didn't have time to explain everything, just come to the Aerial Open Conference in March next year. It will be hosted in Harwell. You're all welcome. The registration is open now. We have a special issue in aerial about aerial that will be published by Rusty, and you can participate to that. And so with this, I hope to see you all in March in Harwell to see some of the part of aerial being assembled in the facilities there. Thank you very much for your attention and time.
Questions?
Thanks for the nice talk, and sorry for a very general question, but Earth-like planets, exoplanets, they are most exciting and they are still largely missing from the picture. So you showed this nice slide of past, present, and future missions to study exoplanets. What is still missing to get even better sample of Earth-like exoplanets and to study them?
Okay, I think there will be talks that are probably more into detection of Earth-like planets. In particular, I'm thinking about the talk on PLATO, and then I think there will be talks about HWO later today. So probably they are the one that should answer better this question. But the point I want to make is that the smaller are the planets, the colder, the more complex they are, the more difficult. If we don't understand the quote-unquote, even from an atmospheric perspective, easier one, chances are that we are missing on the small one, and perhaps on the small one we might see biosignature that are not really biosignature. So I think we need to do a lot of work, in my view, with web, aerial, the ground, to understand better the easier targets from an atmospheric perspective, meaning super-Earths, giants, and Neptunes first.
I'm sorry, I was actually meaning that what are we missing from the instrumentation part?
Okay, yes. Well, HWO and PLATO will probably tell you what is their plan. And so I think they are the best in place really to answer to your question.
Thank you.
Thank you. Sorry, time is over.
No,
so thanks. And the next talk is about PLATO mission by Juan Cabrera. Please.
Okay, so then first let me thank the organizer for bringing me here and giving me the opportunity to present you the mission PLATO. PLATO or PLATO, I mean, 50% of the times I see it in the French way and 50% of the times of the British way. I'm sorry about this. I just cannot decide myself. So, and of course, I'm presenting this on behalf of the PLATO team. Let me skip this one. So, okay, you have seen PLATO on this slide before. That shows which is the landscape that ESA has presented now for the exoplanet characterization missions. I think the important part in this plot for you today is what comes next. I mean, we should not stop here, and we should not let ESA stop us here. We should keep convincing them that there is future to missions that we want to bring and new questions that need to be answered. So, because 50% of the audience are PhD students, it's your work to make sure that we don't stop here, okay? And how does it work, actually? I mean, you need to know this because you might invest the next 15 years of your career in developing a mission. Because this is what it takes. I mean, here you see the timeline for PLATO. It was presented first, well, studies started in 2007, actually, and it was presented in 2011 first time, and it failed the selection, but you are not a real mission if you not fail at least once. So then it was selected later in 2014, mission adoption. I mean, this is very important for you. I mean, most of the changes that will come to your mission might happen between selection and adoption. So make sure that you are ready at the beginning to fight for every camera and for every photon. Then it goes very fast. I mean, 2018 was the contract with the prime contractor building the spacecraft. We got the first CCD 2019, and then started building the models, building the cameras. The first engineering model, the first things that you have to play with were in 2022, tested at the facilities in Netherlands and France. And then in 2 years, we had the first flight models, the real cameras being integrated on the spacecraft, and now all the cameras and all the spacecraft and solar panels and everything whatnot is already at ESTEC. Doing the last tests, some functional, they are shaking the thing, but I'm not worried about this. They are also testing the software. This I'm a bit more worried, but we will do our job. We have 1 more year to fix things, and then it will launch. So now we are waiting for the launcher. We hope that Ariane 6 will make it. It might delay until beginning 27, but it will be launched. And then we have start of nominal operations. There will be 3 months commissioning. And the first data, calibrated data, will come in 2028. I will show later one slide about the data release. Sorry about this slide. I only realized later that I might not have submitted the right version to the organizers, and this is not very good seen in PDF. So what this slide tries to show, I mean, why are we doing PLATO? I mean, what was PLATO has very concrete goals, and this is what drives the design. And this is why we bring you a design that might not be able to do everything, or you might have optimized in a different way. But we want to tell you why we do it this way, and why it's also possible to do other science, but we focus on this very particular one. And the particular one that we wanted to check with PLATO is we want to understand how planet and planetary systems evolve in time. And we want to do this because we are very interested in understanding what happens also in the solar system. In the solar system, we have few planets that we know relatively well, but there are a lot of questions that we cannot answer if we don't see planets everywhere else and see how they behave in different stages of the evolution. And we cannot go back in time. The only thing that we can do is to look for more planets around other stars. And in particular, I mean, there are 2 ways to evolve. I mean, gas giants that you don't see here, they are typically boring because they just cool and differentiate, and it's not boring. There's a lot of science to do there. But terrestrial planets, I mean, the terrestrial planets are much more interesting because they not only cool and differentiate, but they can develop plate tectonics, they can outgas secondary atmospheres, even develop life on the surface. And this is what we want to understand, and by finding other planets. Still, I mean, this, well, going back to the first slide, I mean, when you propose your mission, your science case has to be valid for the next 20 years, because otherwise, when you have your instrument ready, it will have been done already. And this is the case for PLATO. I mean, we knew already in 2011 that it would be very difficult to find habitable planets around solar-like stars, and not only finding them, but also be able to independently characterize them, making sure that this is a planet that we know the mass and the radius. We had a bias 30 years ago from the solar system where you could put planets on categories depending on the radius. I mean, there were the terrestrial planets, the ice giant, the gas giants, that's it. We know now, and you have seen this in this conference, that there are planets everywhere with all sizes, all kind of interiors, all kind of degeneracies. And this is why we need to confirm them independently with mass and radius. And we need to characterize them well, accurately and precisely, because we want to know about the internal structure. And this is the case, it was the case 10 years ago, and it's still the case that, I mean, there are a lot of planets that are expanding up to the habitable zone. We have it there on the, for M dwarfs, very low mass M dwarfs. But for solar-like stars, it's still empty, and this is what we want to cover with PLATO, okay? As far as it goes, depending on which is the amount of time that we have in orbit. And also you see different kind of versions of these slides. It's again the idea, and why I want to do this characteristically precisely. When you look at the radius mass diagram, and you see which is the distribution of planets, again, everywhere planets that don't exist in the solar system. I mean, if you try to see what's going on, I mean, currently we have a lot of uncertainties. I mean, there are two kinds of uncertainties. Here you only see the systematics. No, sorry. Here you see, yeah, you see here everything related to precision of the measurement. Okay, we have measurements on radial velocity that have a certain accuracy on the mass determination. We have measurements on the radius that have photometric noise, stellar noise, and they have a certain precision on the measurement. But you don't have accuracy. I mean, most of what we know about when you see those very well characterized planets, the stellar radii and the mass radii, most of the time they come from stellar evolution models, which are fine, I mean, and it's good, but there is a lot of physics that we want to improve. I mean, I don't have to tell you this about stellar models, and sometimes we might be not taking into account the accuracy. And with PLATO, what we want to do is to have both the precision, the photometric precision, and the mass precision, and also the accuracy, that we can independently confirm the stellar parameters from asteroseismology. And if you look at the mass radius, when you only look at the well-characterized planets, I think here we put 5% in the radius, 10% in the mass. I mean, they look different, and it's different plots, because here, I mean, there is some scatter that is still questionable whether it comes from the observations or whether it has to do something with the internal nature of the planet. And we want to know what happens really in the planets. And when we look at the plot on the right, and it's a bit old, I have to update with new planets, but still, I mean, none of the planets in this plot have more than 88 days, which is the orbital period of Mercury in the solar system. And this shows that we need to go further. We need to increase the baseline of the observations. We need to go for larger field of view, and this is what drives PLATO. The method, you know, I mean, the idea is that we focus in the transit detection and the asteroseismology from the photometry, but we also take care of the radial velocity from the ground. And this might not be your choice. I mean, and it's okay. People still ask us, I mean, why don't you do like TIFOP? Why don't you let the community do the follow-up? And the idea is that we have a very concrete goal that requires very extensive use of resources in order to get, in principle, those habitable planets around solar-like stars. And this might not be your goal. Okay? You're still free to organize as you like, and we want to collaborate. But I mean, in order to reach our goal, okay, we thought it's the only way that we have is to coordinate the community and coordinate the observations to make use of those resources. And also, as Giovanna presented before, I mean, you have to anticipate the challenges. You have to anticipate the challenge of what is the stellar variability will make to your radial velocity signal. And this is, well, one of the, I don't have the references, maybe I should have put some references about this, but this is what is driving also part of the research of PLATO. The teams that are working now in PLATO are trying to find ways to mitigate the stellar variability. In order to mitigate the stellar variability, you need to know better your star. So there are a lot of research that we want to do in this respect in order to make sure that we can reach the goal. And I cannot promise that we will meet the goal. I mean, we are promised that we can do as much as we can. But one of the things that also telling from history, I mean, when GOO was launched, some years before GOO was launched, actually when they were still building the instrument, there was someone in Nature saying that they will not be able to find any transiting planet with GOO anyway, because it's impossible. So when an old professor tells you that it's impossible to do something, don't always trust them, okay? They are wrong sometimes. So very quickly, I mean, as I said, this is the goal. This is what design, drives the design, okay? Why do we need to do it this way? Because we want to detect large number of parameters, including to the habitable zone. We need to collect a lot of photons, but we don't want to saturate our instrument, so we need small cameras in order to have a good duty cycle, but we need a lot of photons, so we have to put a lot of cameras on the payload with the largest field of view that we can build within reason, within the mass constraints and the budget constraints, remember, for your mission design. And the concept that we came with is this distributed field of view on different 4 groups of cameras that they all look in a slightly different direction, but we can combine the light of the same star observed with different cameras. There will be 24 normal cameras that will do the photometry in white light at 25-second cadence, and then will be 2 fast cameras, the ones that you see here on the top, that they are mostly done by fine guidance, so to make sure that we can point the satellite with the accuracy and precision that we need. But they will also observe stars at 2.5 cadence seconds in some red and blue filters. There are some plots to show how it was done. This is the container in which the spacecraft was traveling from in München, the south of München, over Pfaffenhofen to Estek by boat. Unfortunately, we were not there when they crossed the Rhine in Köln. It was 3 a.m. in the morning, so we will not be taking pictures. But now it's in Estek. This is how it looks when they have in this tent. You see people without too many masks, so this is why you have still in plastic. When you see people with more masks, then the thing is not in plastic anymore, but we still have the covers on the cameras, and they are lifting it up. And this is how it looks today. I think and they have now put, I think I have a slide later when they have already installed the solar panels and opened them to test that it works. And I said they are now finishing the test for the mechanical tests and the software to make sure that we can operate the cameras. This is how it looks also in reality. I mean, you have seen this flower plot many times, but this is when we have already known which will be the individual alignment of each camera, at least the predicted one. Things might shake a little bit when we launch. But you see the 4 groups of cameras, and then the different overlap. The colors tell you how many cameras are observing the same star. And there is a little bit of misalignment between the different groups in the order of arc minutes, which is according to the specifications, which means that observing with PLATO will be a bit more fun than with Kepler or TESS or other missions, because you do not always really know how many cameras are observing your star. But in principle, it behaves quite well, and according to what we had in the specifications. There is already know what point in which field we are going to point first. This will be the long observing point in the south. The second one, because the first one was not good enough, so we have to move a little bit also to take some of the very bright stars out of the field of view. We had Sirius before, and this is too much photons for PLATO. And there is possibility also to observe on the north. So the decision has not been taken yet. It will be taken only when the instrument is in orbit and we have measured the performance, and then we will decide if we go to the north or if we stay on the south. And it also depends on other developments like Earth 2.0. I mean, there are other missions that might go to the north, so that they may consider. But the baseline for now is the first 2 years in the south, then there are another 2 years of nominal mission, and then hopefully we get an extension, and then we will either go back to one of the 2 fields or do what we call a step and a stair, where we point to different areas of the sky for shorter periods to cover different kind of science. How we are organized, I mean, there are 3 big areas: the payload, the data center, and the science management. The payload, they are all happy and going back home to work on the next project. As I tell, the instrument is delivered, they are finishing the spares, but it's okay. It's ramping, well, the data center are full speed now. On the ground segment, now we have ESA in the SOC. We have the data center that are building the pipeline that will reduce the data on ground and will produce the data products that I will describe later, and the science management is the one that are, let's say, preparing the science and exploitation that comes later. The number of stars, this is one of the key criteria that define the mission. I mean, there are different samples that we call, depending on which is the photometric precision that we achieve and the kind of science that we can do. We focus on F2K stars because these are the ones that we want to observe for the Earth-like planets, but it's possible to observe all other stars with PLATO, of course, but they will go into the guest observer. So the consortium doesn't own all the science or all the targets, but only focuses on what we have to do on for a goal. They will be brighter than 11. About these numbers, the requirement was 7,500 per pointing. And of course, when we do another pointing, then we will double this. And the noise level, let's say less than 50 ppm in 1 hour. I will show later what this means. The P2 is a bit brighter sample, as a set of the P1. P4 are the M dwarfs. There are 12,000. It's unclear that we will observe all of them because they tend to be faint, and it doesn't make sense to use PLATO to observe faint stars. And the P5 is also solar-like stars down to magnitude 13, where we have especially a more statistical analysis of the populations. I would like to point your attention to this paper from Valerio Nachimbeni, where he shows all the different kind of what is known about the field right now. I mean, about if you want to know if there are already transiting planets or not planets not known to be transit, or do you want to do, I don't remember what this is. No, this is only the planets, but you can also find information about stellar clusters, about different interesting associations that you might want to observe with the paper. With kind of data, okay, so as you imagine, we cannot take full frame images and take them to ground at 25-second cadence. This is too much telemetry, so we have to do a lot of data processing on board. It will be a mixture between what Kepler and TESS did and what Kogo did a long time ago. So for the bright targets, everything brighter than 11, we'll have images, or the postage stamps in the Kepler jargon. So we get pixel information, time series of pixel information at 25 seconds. For most of the P5 sample stars fainter than 11, we will compute aperture photometry on board, and we will only download the Likers. If we happen to have a transit on this Liker, we can upgrade to an imaget, but from the baseline will be Likers. And let's say that each set of data from the 3 months observation will be made available 6 months later. So why is this? I mean, first, we will release the calibrated data, and calibration requires that we compute the detrend instrumental systematics. In order to detrend instrumental systematics, we need a full chunk of 3 months of data to make sure that we can compute the coded trending basis vectors and whatnot that let us improve the data. And this takes time. So the validation takes part on ground, and when the data is validated, then it's released to the community. And there is also the possibility for the community to apply for their own targets. They will be reduced in the same way and delivered to the proposers. And it's 8% of the telemetry is available to the community. There is a workshop soon in München about how to prepare your proposal. And there will be a call issued by ESA on March next year so be ready to propose all your targets, all the stars that are not included in these FGK samples that are interesting for you. You can do this at that time. This is the different data levels. So this is level 0 is as it comes from the satellite. Okay, so we have the images and some validated Likers, but they will still have a lot of systematics, and also they will be produced at camera level. So we will start 24 or 6 to 24 times the same course for the same star. Level 1 is when we have reduced all the systematics that we know, and then we provide the data products not only at camera level, but also at system level when we merge the Likers. This will be probably more interesting for you. But PLATO doesn't want to stop there. I mean, the idea of PLATO was not to stop at the Liker and let the community. The idea of PLATO was to deliver a catalog of planetary candidates and a catalog of stars characterized in an homogeneous way. So this is what makes the difference. This is the level 2 data products from PLATO, which are not only the transiting candidates, but also the results from the astroseismology, rotational periods and activity, stellar masses, radiant ages, and also the transit timing variations. And this is the trove of PLATO. I mean, this is where you come and you say, okay, I want to do my science. What do I learn from this? How can I correlate? How do I don't know, answer those questions? I mean, one of them, was presented already here. I mean, we want to know precisely the interior structure, also to understand the evolution, but there are degeneracies. How do we sort out those degeneracies? How do they depend on age? Is there any way to link the interior composition to the atmospheric composition? I mean, we don't have the answers now. It's up to you to find those answers. And then the level 3 is once we combine the ground-based observations for the transiting planets, then we have also the radial velocity and the independently confirmed masses. And again, from the release, the statistical sample, I mean, everything that this, most of the data will be released as it comes after it has been validated. Okay, so then you have only for the first quarter we have 6 months validation instead of these 3 months. This is why even if we launch in 27, 3 months commissioning, first data come in 28. And then every quarter will be released 3 months or 6 months after the start of the observations. There is a prime sample that it will take a bit longer to be released. This is for the people in the consortium. This is where the consortium commits to do the follow-up. So we will not do follow-up for every target on PLATO. There is room for the community. There is room for other science cases. But for the core science of PLATO, the ones that want to reach the habitable zone, this will take a lot longer to release. And then there is also a 300 proprietary sample that is for the, it takes longer. I think it's quite similar to this, but this is 300 targets from 250,000. So I don't have time to go through all my slides. I talk too long. Yeah, I don't know. Let's skip this. How do we present this from the point of view? I mean, one of the criteria that allows you to understand what is possible with PLATO is the signal to noise ratio budget. I mean, if you have, start with large noise, let's say, allow you to detect some kind of planets, but doesn't allow to do all the fine characterization. You need to go to low mass. Okay, so this is the 100 ppm line that you have in 1 hour, and here we are comparing PLATO with Kepler and TESS. So for Kepler and TESS, they are real measurements, so they include stellar variability. For PLATO, it's only what we have now in the models and doesn't include stellar variability. So it's a bit unfair, this comparison. You might think that part of these columns will go back to the right, but still, it's a logarithmic scale. What I want to bring you, I mean, what makes different PLATO from previous missions. Here, I mean, the science that you can think is about giant planets, okay? So you can do ice giant planet population studies and seismology for giant stars. You cannot do solar-like stars here, which is the advantage here. I mean, you have a longer baseline than TESS, okay? Here you have the 50 ppm line. Here you can do smaller planets around big stars, okay? And again, here you have the longer baseline that is the evolution and seismology of evolved stars. But now when it starts to get interesting is we go below and the 30 ppm line, and this is when you want to detect the Earth around the sun, okay? It's possible with TESS if it were not because of the 27-day characterization. But then, I mean, this is what I think will also be very interesting, and this makes a difference when you see which is the field of view of PLATO and the amount of bright stars that we observe. I mean, here is where we expect to have unprecedented photometric precision on a large number of stars. And let's see what we can do here on new science. It's up to you to propose. And this one pointing for PLATO. I mean, for TESS and Kepler is everything that has been done. I mean, up to 28 in TESS and Kepler, everything. And for PLATO, this is one pointing. I mean, we hopefully have either a longer baseline on the same pointing or more pointings distributed over the sky. I will skip part of the ages because I don't have to convince you why it's important to have ages in the stellar community. In the planetary community, they sometimes need this slide. But this is the last one. As I said, this is when you see the solar planet deployed. On simulator of zero gravity are those things that you see here. So they hang the solar panels, and I'm happy to take any questions. Thank you for your attention.
Questions, please? So this one?
Hi. You stated at the beginning that a mission may be something that we do for our whole life because it takes a long time. How do missions adapt to new discoveries? Like, they don't get outdated while they're being planned?
So I'm not sure if I understand the question.
So since a mission takes a long time since the start planning till it happens, maybe discoveries happened along the way, and how do you avoid your mission to get outdated when it starts?
Well, I mean, it's great when new discoveries come anyway, because we always learn something new. I think you have to be ambitious. I mean, you have to focus on in the end, for all these missions, as Giovanna presented before, or we have a consortium about 1,000 people working for 10 years on the same goal, and this is a lot of investment. So you have to be ambitious on your goals and make sure that you have something that is worth the effort and the investment. But there is no magic rule.
More questions? Actually, I have one.
Okay.
I understand that PLATO will have a list of stars, the targets which you observe. Okay, I look at this list and I see that my favorite is not there. What can I do?
So if you are part of the consortium, you can still talk to the people presenting the catalog, and we see what we can do. The catalog will be released to the community beginning of next year. So in principle, we can still update, although they will hate you. But, and if not, as said, there is the guest observer program. So anyone in the community can propose their own targets. And the only thing that is required that they don't drive the operations. I mean, we cannot point the satellite in a different direction, and we will not include new data processing methods for you. But in principle, any target that is on the field of view will be, it's accessible.
So it's that it can be extra downloaded,
yeah.
Because not everything is downloaded, right?
Correct. And this is done by ESA. I mean, ESA is not in the hands of the consortium. ESA will form a time allocation committee. They will evaluate the proposals based on scientific merit, and then there will be time awarded to the proposal.
Very nice, thank you. More questions?
We will also provide the tools how to know if your study is observed or not, and which signal to noise to expect.
Thank you. So, thank you again. Next talk is from Ana Inés Gómez de Castro, and she will talk about amazing facility, the Habitable World Observatory. And Anna is online. Well, it was not possible for her to come, but we did not want to omit this important presentation. So, Anna, please, the floor is yours.
Okay, thanks a lot for the invitation. It's a real pity not to be there. I would have loved to. We see so nicely also in radio frequencies and in the infrared. So what is nice also about this picture is that you have basically the dominant tracers to study each one of the components, and though there are many in the infrared that are fine, we have good coverage with current instrumentation. There are many that are in the UV and X-rays, and you know that we will need to improve our instrumentation on that fields. And that's where HWO is going to open a completely new frontier, because HWO will be an 8-meter ultraviolet space telescope. I mean, will be ultraviolet, optical, infrared, it will do coronagraphy, but it will keep the ultraviolet window open from their launch on, because for many years now, we will be without access to the ultraviolet range. As soon as Hubble is decommissioned, there will not be access to this range. Okay, so some open questions come here. This comes from one scientific science case that was put by the European community to the Hubble Worlds Observatory that was related with the topic that you are addressing in this Congress, and that, by the way, is my research topic, which is, well, star formation, magnetosphere, launch of jets, etc. And this, which is the topology of the Titauris magnetospheres. How does it relate with the accretion rate? How does it relate with the stellar mass and with the presence of nearby companions or not? And here we could even put hot Jupiters or nascent hot Jupiter or large planets which are close to the star. Then there is the part of the wind, how winds and outflows are generated. Still, we don't know many things. Which role do they play in the efficiency of accretion? And also, well, which is the UV radiation produced by this phenomena, which is the one that affects the whole disk evolution, including the formation of the planets. So for the magnetospheric accretion paradigm, you know that now our colleagues using SPIRU and some other instrumentation are being able to reconstruct the magnetic field of some few stars, but only some few stars and only in the optical range. So they know the photosphere, but they don't know how the photosphere links to the chromosphere and the large-scale magnetic field that is driving the accretion. And what we are finding is that the magnetic fields are variable. Some sources are better behaved, like for instance, EY tau, which is a very dominant dipolar component that changes in strength and slightly in inclination, but more or less goes okay. And others are a bit more crazy, like you have a BP tau with this dipole and the octopole and how they are managing the accretion flow. We need to study that. And well, so most of the radiation, as you see here, and most of the information about this accretion is in the ultraviolet. And well, with the ultraviolet, we are seeing how the pre-main sequence stars compare with main sequence stars, and we are finding intriguing things about the dynamo. Main sequence stars are fully convective stars. These are fully convective stars. These are not. So still we don't know, and this is a completely open field, how the transition from the fossil to the dynamo field is made, and which are the implications for the future stars. And well, these are the latest results from the Ulysses dataset that has been covered, I guess, I think so, during the conference, where you can see that we are getting amazing results and also a lot of puzzles, because this was supposed to be a rotationally modulated light curve produced by these are UV lines producing the accretion shocks. And as you see, the rotational modulation is not obvious, let's say, okay? So this is a big part of the problem, and this is the relation between the very easy beginning of the subjet simulations, where you have a nice dipolar field, and this is when you start to complicate the things, and this is when you still, when you see which is the impact of these complicated topologies on the inner disk producing these warped structures. And also, well, we also need to learn more about the outflows, where do they depart from, and the relations that they have with the chromospheric energy release in the star, and accretion, and the angular momentum problem. Okay, so well, these are some simulations that show that there are plenty of regions where magnetic reconnection occurs. And in these regions, when you have magnetic reconnection, as occurs on the sun, you will have ejection of plasmoids that will become the nodes that we see propagating in the jets. And the situation is very rapidly variable, as shown by these lines. These are predictions of the emissivity in the carbon-3 lines. Okay, so still we don't know many things. Still, we need a lot of data, especially in the UV, but also panchromatic view, a simultaneous view from the UV to the infrared. And we have been studying these outflows, and we have come up from indirect indications like the terminal velocity of the wind, that they come from the disk, not from the star, but that's the only few results that we have up today. And Still, we have pending another issue, that's the use of binaries, and for the understanding the accretion process, and also for understanding how matter falls onto the star, or flows from the inner border of the disk to the star. This is a nice example. This is the molecular hydrogen variation during the falling of material to an accretion shock on the star. This can only be properly timed in a binary system where the accretion flow is enhanced close to the periastron. And here what you see is that the hydrogen 2 flux, the UV hydrogen 2 flux decrease, because this line is pumped by Lyman alpha, and the Lyman alpha radiation is blocked by the stream that is falling onto the star. Okay, so, and then well, we have a completely open question which is related with polarization. Polarization is crucial to see dust nucleation, to see large molecules, especially at the UV, that's the relevant wavelengths. And that's it's a game changer, but still we don't have those facilities. Among other things, because we need larger collecting surfaces to do the same kind of studies in polarization, in spectropolarimetry, that we do on normal spectroscopy. This said, let's go to HWO. Okay, so before HWO, there was a pre-existent UV community in Europe that was putting forward a large mission that was called the European Ultraviolet Optical Observatory, and that has kept the community together for many years, and you are all most welcome to join in. The community is now coordinated under the network of ultraviolet mission, and if any one of you is interested in participating in these activities, please contact me, send me an email, and you'll be rapidly added to the group. So the idea was to have a large observatory with full capabilities to do simultaneous and optical observations, and with a collecting area of at least 10 meters. This proposal didn't go ahead, and we are still, we were pushing for that before HWO. Now that HWO is in the NASA system, what we want is to collaborate, obviously, with NASA. And these are the 3 science teams that are prioritized by the European Space Agency, which are the moons of the giant solar system planets, the exoplanets and the galactic ecosystem. We have just heard about PLATO, and then the new physical probes to the early universe. Well, but this is the NASA system, and as you see, they pair very well. No, exoplanets, solar system, cosmic origins. And the recommendation from the decadal review that was several years ago was to put forward in the US system, then in NASA, a large mission that was able to accomplish the first observation of an Earth-like planet. That means coronography accompanied with a spectroscopy, very low dispersion spectroscopy, that will operate from the ultraviolet to the near infrared, the ultraviolet to get the ozone blocking frequencies, and to reach into the near infrared, and to get the molecular bands. But also, in the same report, it was stated that this mission had to be an observatory capable of doing many scientific projects. And that's what is becoming HWO. So HWO currently, well, this is not the current design, this was one of the first telescope designs, but it's a telescope that is between 6 and 8 meters. If you talk to the engineers, they feel happy with the 6 meters. James Webb, the control is already a challenge to be able to do coronography and work at the ultraviolet wavelengths. But on the other hand, the scientific community is pushing strongly to increase the collecting area, as you may guess, and we are pushing for the 8 meters, and there we are. And HWO is designed to have 3 main instruments. One is a coronagraph to obtain images like this. This has been a challenge, and there are a lot of discussions between European and US-based communities on the participation on this coronagraph, though it is very clearly an instrument that will be led by the US, by NASA system. The other instrument is going to be a high-resolution imager, wide field, as you see. And this instrument is being thought in a general manner, still not proposal. I will get back to that. And then the other one is a UV multi-object spectrograph, which is called LAMOST, the name that has been used, that will be providing integral field spectroscopy using microshutters or image slicers, still unclear, to work on the bandpass from 100 to 1,000 nanometers. And this said, there has been operating some science working groups. The news were passed all over the European community to enroll them because these science working groups were operating at global scale. There are people from all parts of the planet, though the largest community are obviously the US community, and the second largest is ours, is the European one. And the groups were organizing these 4 subjects, including living works and solar systems in context where a lot of work was done on the formation of stars, also in the stars and stellar populations, star formation. So our field, the field that is addressed in this conference, is touched at least in 2 or 3 of these blocks. And they came up with science cases. Okay, these science cases were specific. It's like when you make a proposal, but an open proposal. I want to address this problem. This problem is crucial because of this, and I need these particular capabilities in the instrument. I need high resolution. I need sensitivity. I need spectroscopy. I need spectropolarimetry, whatever. Okay, so these science working groups have been working for a year and a half, nearly 2 years, and their work ended last July. And last July, at the end of July, there was a big meeting in Washington where the results of the working groups were presented and the last designs were presented, and all of this was discussed. And well, at that time, this was the people who participated. There were more than 1,000 scientists all over the planet. And as you see, well, the countries that were most involved in the world apart from the US were the European countries, and very especially France, UK, and Spain. Okay, here is the distribution by countries. And well, these are the 3 then Germany, Austria, Italy to a lesser degree, and then many other countries in a much lesser degree. Okay, and the current situation is that taking together all these SCDD, science case development, okay, taking into account the science case and taking into account the telescope, which includes the telescope, the coronagraph, and the UV instruments, some key technologies have been identified, and the coming years are going to be devoted to the trade-off analysis for these for these instruments. So critical issues relate with coronography and the requirements for the telescope related with coronography, and also with the UV, the high quality that UV requires. So there is research on UV coatings, mirrors, and the construction of a near UV coronagraph. There is discussion on the coronagraphs and the detectors, and also on the UV shutters arrays. Okay, and which are the ongoing European activities? Well, there are many ongoing European activities. There is a group, I don't know you are aware, I don't know whether you are aware, which is called the High Contrast Imaging Group that is already collaborating in the coronography. There are groups that are working on multi-layer coatings for the UV, that the technologies are being actually, European technologies are reaching high TRL through NASA flights. There are some technological probes, like the UV polarization mission by ECNES, CASTOR. And there are science probes, like the Lunar Ultraviolet Observatory to observe the Earth as an exoplanet in the UV. And there are also activities related with putting forward proposals to get spectropolarimetric data and to initiate this activity. Unfortunately, this proposal didn't get through, but it was participated by many European and non-European countries, and we expect that we will be more lucky in the next call. And then there is this big project. POLLUX is an instrument which is a very large spectropolarimeter. It's led by ECNES. And this gives you an idea of why I say a large spectropolarimeter. And it will work from 100, not to 400. Now the current design is to 1,500. So well into the J band, in the H band, in the infrared. And we'll have a dispersion of about 100,000. The design drivers are exoplanets, interstellar medium, and being able to do this polarimetric map. I was talking at the beginning from the photosphere of the star to the chromosphere and all the envelope of the magnetosphere in T Tauri sources. And the project is open. If you wish to join the working groups, please join, call me and or send me an email, and we will easily include you in that if you want to participate. Okay, and then just to summarize a bit, the current situation is at the beginning of the process, you know that ESA nominated 3 scientists for the START, this science and technology group that started creating the science case and the first technological designs. The 3 people were Michel Min, David Mouillet, and myself. We were selected through competition, so people presented to be candidates, and then some of us were selected. But our term is finishing now because this first step, the START, is finished. It's finished in July. Then the other aspect that is important for you to know is that ESA has compromised to contribute an instrument to the size equivalent in size to an M-class mission. But this funding will not go through the main calls of M and F class missions. It will go through an independent call related with international collaborations. And the key time is this. You know that the ESA Council is in November. And then there will be, at that time, we will know how much money ESA has, and then it will start making the timing to go ahead in the project. In the meantime, the community is enrolling in different groups, and also the national space sciences in Europe are organizing in several groups to propose even more, propose instruments to a potential ESA call that is expected to be early next year, to start defining the designs of possible instruments, European-led instruments for HW. And this is it. I think I hope I am on time. And if you have questions, obviously, I am very much open to them.
Forward science cases and groups for this habitable world observatory. Am I correct?
Okay, there are two processes. One is the NASA-led process, the US system, where they did all this work, and that was the one that ended in July. But then now, Europe, if we want to put forward instruments, we will have to make our own science cases. Okay? So the process is still open on the future instruments that Europe can provide to the project. So in that sense, for instance, for the POLLUX instrument, there are some science working groups that are creating proposals for instrumentation that you may enroll in. And also, well, the collaborations with our US colleagues keep open, okay? But NASA needed to have this definition of basic science cases to set up the envelope of the telescope, because it's a real engineering challenge.
Thank you very much. More questions, please? Yes. Yeah.
I mean, you have mentioned Pollux, which is one of the possible contributions from Europe to the payload, but could you give us more details about other initiatives in Europe proposing, or there is only Pollux coming from Europe?
No. There are many, and I think that there will be more. Okay. But for the time being, what is, as the ESA call has not come up, it is unclear which are there, and I didn't want to get into a list just in case I forget someone. To my knowledge, there are proposals to make a European version of the LAMOST instrument, integral field spectroscopy, low dispersion from the UV to the infrared limit. There is another proposal that is quite strong on coronography, on participating in the coronagraph that will be led by the US, but there are European groups that are already collaborating with the APL on that. NASA will be very much interested in the participation of someone in the near UV coronagraph, the one that will get the right cutoff to observe the ozone window. And also there are some initiatives, to my knowledge, to produce a wide field emitter with a large CCD. So this is what I am aware of. There are many technological conversations between groups in Europe and the US, people who develop instrumentation in different countries, doing different things. The one that I know the best is related with the coronagraph and this high contrast imaging network I mentioned, and also the UV coatings. That also is a group that resides a bit in Spain. And these are the two that I know the best. But I think that to have a full view of what is going on, we'll have to wait for how the groups arrange around once the ESA call is issued.
Thank you.
Thank you very much. More questions? If there are no more questions, let's thank Anna again. And now we have a coffee break, and we will be back at 11:20.
So we will not wait for those who are late, and we will start. Daniel Langerhausen will give a presentation about the life mission, which will be no, I cannot pronounce it. Anyway, looking at the rocky worlds. Thank you.
Great, yes, thank you to Anna and the SOC for inviting me, but also thanks a lot to the local organizing committee, so for the patience with all my, when I was too stupid to find the right link, 5 minutes later they send it to me and uploading so really great work, so yeah, free feature applause for the, for the LOC. Yeah. So I actually have to start with a confession, so I'm technically not part of the live team anymore since beginning of this year, so some of the information might be 6 months outdated. So, but I hope this doesn't change a lot. That also means that not necessarily job market, but I definitely have a bit more free bandwidth for projects. So if you have any ideas, how my weird expertise could help your project, you want to write a proposal together, just reach out to me. I have a lot of free time at the moment. Okay, so for today, I plan to give you a bit of a top-level summary of this life in all caps. How life looks for life, a bit about the heritage and the roadmap, and a bit of the technology, so where we are coming from, but not too much. I know it's not an engineering conference here. Then I will introduce you to this measuring principle of nulling. So I call this part nulling for noobs, and don't worry if you don't get it, it's a pretty tricky concept. And then I will really talk about the science, so the life detection yields, how many exoplanets we will detect, and also how we will then characterize these mostly terrestrial temperate exoplanets. And then I want to focus really on how this community could help. So I talked to Anna, and I obviously paid attention the whole week and was thinking hard about how people with their expertise here, especially the younger folks who might be the ones who actually use life, could help this community. And then if some time is left, I might even be able to tell you how life could detect alien civilizations. As an affiliate of the SETI Institute, I always need a slide like this in there. So let's see if we get there. I want to start with something to inspire you, so to give you an idea what we could observe with life. So this is 2 papers that we just submitted or is in the process of submitting. So this is 4D spectroscopy, if you want. So spectroscopic phase curve of Proxima b. So we simulated that, and admittedly, it's the closest neighbor that we have, so one where we get the biggest signal to noise. But you can nicely see this is for 1-to-1 resonance, so a tightly locked planet. You see how the day side of the planet appears. You can even see at 9 micron the ozone feature disappearing and reappearing, so a biosignature, potential biosignature gas that comes out and goes away again. So just as an inspiration, what your generation could be observing in 15, 20 years maybe. So just as my generation was dreaming of PLATO and Ariel, and now we are close to getting this data, this is the data you might get in your future. So really use this as an inspiration, and also keep this in mind. I will come back a bit to this later, for what would be possible. So really there's no limits to your imagination what you could observe in the future. This is maybe the super top level take-home message here. But also I want to come back and tell you exoplanets are hard. So just a couple of weeks ago, we had this landmark 6,000 detection, and we are celebrating the whole summer again and again that Didier and Michel found the first one 30 years ago. So it sometimes sounds easy, right? Nowadays you can even take transit observations with your phone almost, but it's still hard, especially if you want to go to terrestrial exoplanets around sun-like stars. So this is real data of a transit of Mercury in front of the sun. So this is a transit of a Earth-like planet around a sun-like star. And this gives you an idea how hard this is, right? This challenge that we have. We want to observe these tiny little black dots next to these big balls of fire, right? And this might also give you an idea that transit might not be the best technique, at least to do spectral atmospheric characterization of these planets. So this gives you an idea. So really, first problem we have, we somehow need to get rid of this star if you want to separate the light of this planet. So this is the first challenge. And then even if we get rid of all this noisy starlight that keeps us from looking at the planet, even if we get this tiny blue dot separated from the star, it's still a very, very, very faint signal. So if you look at an Earth twin at 10 parsec, you get 1 photon per minute per square meter per micron. So if you have a 1 square meter telescope, you get 1 photon at 5 micron, and then you wait a minute, and then you get the next photon. So you can give every photon a name if you want. So this is really shows you how tough this also is, not just in separating the starlight, but also that even if you separate it, to count these very few photons from these stars. And this is where life comes into play. So this is the slide that has sound. So just for the folks in the background, let's see if that works. Yes.
Life, the large interferometer for exoplanets, is designed to address this question by collecting infrared light from distant worlds. We know of thousands of planets orbiting other stars, and life will help us understand their diversity. For the first time, we will be able to tell if some worlds are similar to Earth. With atmospheres containing molecules such as methane or oxygen that may indicate biological activity, our team is dedicated to discovering if life beyond Earth is rare or a widely spread outcome of cosmic evolution.
Yeah, so this is the life mission in a nutshell. So we paid a lot of money for this video, so I have to show it at every conference. So apologies if you have seen this before. So to put it a bit more into, let's say, political or international context, so also following up what we heard in the past presentation. So there was this ESA Voyage 2050 roadmap, senior committee report, somehow similar to the decadal, not as binding as the decadal report in the US. But in this report, the senior committee recommended that atmospheres of temperate exoplanets in the mid-infrared should be a top priority for ESA. It would solidify the European leadership, would be an outstanding breakthrough. So in the life community, we take this, let's say, as a mandate to look into a concept like life, to potentially become this L5 mission for which this theme was suggested. But we're also looking in alternative ways. So similar to what, for example, Giovanna presented with, running independent consortia, going through philanthropy, through crowdsourcing or whatever. So we are open to all kinds of ways to, use the changes in policies, the changes happening in new space at the moment to do this maybe a bit different from your grandmother's space mission, right? So we are open to both. We're open to ESA as well, to alternative ways to build this, to make this happen. In a nutshell, so what we are thinking about is at the moment, four collector telescopes. Right now we're looking more at the larger version actually with 3.5 meter mirrors, about 100 to 600 meters in difference in this rectangular formation, which then combine their light in this 5th combiner spacecraft with about 5% throughput that we're working on right now. And what we are trying to get is spectra in the mid-infrared of these exoplanets from 4 to 18.5 micron at a resolution of hopefully about 100. And then nominally we are thinking about half of the 5-year mission timeline to do a search phase, so really scan our neighborhood for these terrestrial planets, and then another 2.5 years to really deeply characterize them, look for spectral signatures, biosignatures, study the diversity, assess their habitability, and really just study this diversity of terrestrial planets. So quite similar to what we might be doing with hot Jupiters right now, which we might be doing with sub-Neptunes in the next phase, do this with rocky planets. And if it turns out that, let's say, high precision radial velocity or other surveys already give us enough Earth-like candidates, we might even be able to skip this search phase and directly go to characterization. So this is really just to be kind of like self-sufficient in a sense. Then again, if we get these black tiny blue dots, we will get spectra of them. And then in comparison or in synergy with habitable worlds will look at the reflected light of the planet. So the starlight being reflected from whatever is the top of the reflecting top of the exoplanet. And then with life in the mid-infrared, we would look at the actual own emission, thermal emission in the mid-infrared of the of the planet itself. And it's really complementary, so it's not that we are competing with HWO, and I think everyone who's in this topic agrees that this is really, in the ideal case, you would have both missions. There's a nice paper by Eleonora LA. He really works on the value of combining these, just as a bit of an overview. So there's a bit complementary in terms of molecules we can observe. So while Habex and Luva in this case, which then became HWO, are not very good at getting CO2 and methane, whereas life is not as good as getting O2. What's also really good about life, because we look at the actual emission of it, life is very good at getting the radius and temperature, which is a bit tricky. Some might know, you got this big degeneracy in the optical. Is it reflected light? Is it high albedo, small planet, or low albedo, big planet? So we can break a bit of this degeneracy with life. So really, as I hope I can convince you, a complementary thing. A bit of the heritage. So some of the older folks in the audience might remember some of these older concepts. So there was this TPFI, 20 years ago, TPFI, and then also the Darwin concept here in Europe. So this is really not a new idea. So we didn't came up with that from scratch, but we re-evaluated it. So we looked at all these new exoplanet statistics we got from Kepler, and I will show you in a second, how many exoplanets we would find, which was one of the skepticisms about Darwin. Obviously, a lot of progress was made on the technology side, which we can adapt now. So this is really, built on the shoulders of giants. So really there's generations, or at least one generation of really, really smart people who already looked in a lot of these problems. So we are not really starting from scratch in that sense. And just as an overview, I know this is not an engineering or optical engineering audience here, but there's a bunch of technologies that we are still have to tackle, have to fill these technology gaps. It's formation flying. Of course, we want to have, know how to, navigate these different spacecrafts with each other. As I mentioned, we need detectors that can collect this 1 photon a minute. We need to make this all these cryogenic parts, because we want to observe in the mid-infrared, so our instrument needs to be cold. And also we want to combine 4 beams, maybe 8 beams, so we also need very sensitive ways of combining these beams. So just very top-level overview of these technologies we need to develop for this. So then how does this whole nulling interferometry work? And this is maybe a bit of magic. So I hope I can give you at least roughly an idea how this nulling works. So first order, if you take 2 telescopes, it's a bit like a double slit experiment. You can see here you get this interference pattern, which you might remember, from physics in school when you get your electrons to the double slit. Or if you do like classical interferometry, typical, like maybe with ALMA or with radio telescopes. But then the first trick is you do a phase inversion of, let's say, one of your arms. And then you just flip this from, constructive interference to destructive interference in this center here, where you have your star on axis and your planet off axis. So suddenly your starlight gets suppressed, whereas your planet is in this one stripe that has transmission. So that already kind of like cancels out the star, but it's still not easy to get the planet. So the next step we do then is we rotate our array. So then we move essentially the planet, so the star is canceled out here in this black area, and then we move our planet, or we move our telescope, and then the planet moves in this transmission map, and then we, in the end, get this actually a time series observation, and that becomes maybe also important for you later on. So in essence, it's a time series observation of the planet moving through this transmission map. And then level 3, if you take even more than 2 telescopes, these transmission maps become arbitrarily more complicated, but keep in mind it's a time series observation of this planet moving through this transmission map, which suppresses the star in the first order. And if you didn't get any of this, I also didn't get it, so it took me like 2 of the 5 years in the live team to actually get an idea of this myself. So I'm still sometimes wake up at night and these flux units are haunting me, so don't worry, you're not alone if you didn't get this. Okay, getting that technology part out of the way, let's talk about the science. So how does life, or what does life detect and characterize? Mostly on these terrestrial temperate exoplanets, but also in other science cases. So there's a large series of life papers. So I really recommend you to put life interferometer into archive or ADS and look for them. So 14 official life series papers and many auxiliary papers, let's say. And in the next couple of slides, I really want to summarize the most important ones, maybe all the most relevant ones for this audience. So the first one, and this is kind of like where we started, is how many planets would life find? So I mentioned before, when these previous concepts, Darwin, TPF, were suggested, we didn't have an idea if planets even existed. That was before Kepler. We had no ideas of occurrence rates, if Earth-like planets are, a percent or maybe even less frequent. So the first thing we did is calculating how many planets would we detect if we were completely on our own, just to be self-sufficient. And don't look too much at the absolute numbers. So this obviously changes if you use, more throughput or larger dishes. But in essence, the thing is we get hundreds of planets, dozens of these temperate rocky planet ones, and most of them exclusive with life. So not necessarily observable with HWO, especially for the later type stars. So this is probably already interesting for you. So while we are obviously most interested, as the name says, in these exo-Earth twins, we will get a lot of sub-Neptune, sub-Jovians, maybe even a handful of actual Jupiter twins. And I think this is probably maybe even more interesting for people working in planet formation. There might be these Rosetta Stone planets who can solve planet formation if you get the right temperature giant in the right orbit. So this might already be very interesting for you to get, C2O ratios of hundreds of sub-Neptunes. Might be pretty cool for you, I can imagine. Just a bit of an idea, we are really talking about our closest neighborhood. So comparing bulge to thin and thick disk might not be possible. So this is really targets in our closest neighborhood. So for the M-star planets, it's really like 5 to 10 parsecs, so really our closest neighbors. And then if we go to FGK type Earth twins, we're looking at maybe 10 parsec, 20 parsec, maybe out to 30 parsec, depending on how big we point our telescope, but really our closest local neighborhood. Then after we found them, so let's assume we get these, characterization phase, we have, let's say, 50 potential Earth-like planets in the habitable zone. Then what kind of characterization can we do? And the first kind of sanity check we did was really checking could we detect ourselves. So we took the solar system and put it at 10 parsec and then looked, would we be able to detect Earth? What can we tell about Venus? Would we distinguish Earth before the oxygenation event versus an Earth after it? We also have a couple of papers on using actual mid-infrared data from Earth and simulated it as an exoplanet. So there's a huge body of work already showing that we would be really good in, seeing ourselves. So really, if we had an Earth twin at 10 parsec, we would be really good at characterizing this. And then we also had a bit of work on life as we don't know it. So we're looking at a bunch of these potential biosignature gases, phosphine, methylated halogens, nitrous oxide. So all these spectral fingerprints of potentially biogenic gases. Also, again, because we're observing in the mid-infrared, where a lot of these gases have very strong absorptions, we should also be able to detect these also in, more super-Earth, mini-Neptune context, not necessarily only for, rocky planets. Then we went a step further, so not just looking at individual targets, not just looking how good can we observe an individual Earth, how good can we, maybe find phosphine on an exovenus, but also can we detect trends? Can we maybe prove the habitable zone concept? Can we, detect, some other trends in these populations, and then just to see if this yield we have is large enough. So is 50 planets really enough to learn about the universe? And long story short, the answer is yes. So there's this really nice paper by Janina Hansen that just came out this summer. So we might actually be able to test this habitable zone concept so that, with higher incident flux, you also get a lower CO2. So this kind of like greenhouse effect driven by plate tectonics. So if that really is a thing, we should be able with 50 planets to detect this trend. We might even be able to distinguish between biotic and abiotic, as you can see here. So, but maybe not with 50, it might be a little bit too small number, but this definitely also shows that life can be an HWO2 because, you know, it has a similarly large yield, large number of planets to be observed. So it can also be a statistical machine. Another thing we looked at in this context, so was a little Bayesian exercise we did. We were looking at the significance of a null result. So let's say we observe these 50 planets and we don't find life on any of them. Of course, a bit disappointing result, but we could still learn something from this. And this is what we kind of tried to find a metric for there. So first of all, we, with 30 to 50 planets, we should be relatively independent of our priors. So either if you're optimistic to find life before you start, or more pessimistic. So no matter what prior you start with, after 30 to 50 observations, if you don't find anyone, I guess anyone is going to be pessimistic after this. So this is what we showed. So we are quite independent of priors. And then it also shows, let's say, if we observe 30 planets, we don't find any life as we know it, we can really put strong limits on this eta Earth or eta habitable or eta life, this frequency of planets that have life, at least in the way we define it in our scientific question. So in that case, let's say for 30, we could really put a 99.9% limit that the number is smaller than 20% here. So this also shows that life and HWO2 in this paper have this statistical power too. So really a good argument to go for these number of exoplanets. Then briefly some other signs. So there's other signs we looked at that might be interesting for this community. So there's a paper by Markus Jansson on exocomets. So we should be able to observe exocomets with life. There's a nice paper about terrestrial protoplanets with life. So this might also be interesting for this community, that we can observe, these planets in the making with life. Technically, life is also, a mid-infrared interferometer in space, so there might also be an imaging mode. So think an ALMA in space at a somewhat shorter wavelength. So there might also be some disk signs we could make. And as I promised, I want to talk about the aliens too. So before we get to an end, I promised you the aliens. So we even have a paper with Eddie Schwieterman and Ravi Koporapu and some of the usual suspects in this technosignature field. So we modeled these atmospheres with these technosignature gases. So technological gases that you can produce naturally or abiotically. So these SF6, CFC, so the stuff that we accidentally put in our atmospheres. And we showed that they are actually really easy to detect. So the idea is here you have a civilization at the outer edge of the habitable zone, it gets too cold, and then they put all these mid-infrared absorber technological gases in their atmosphere to make it warmer. So what we do accidentally, they do it on purpose. And then a bit by design, of course, if you increase the mid-infrared absorption of your atmosphere, it's obviously also easy to detect in the mid-infrared. So it's a bit of a thought experiment. So I'm not saying you that we will find aliens with life, but it shows you how powerful this instrument is. So it's powerful enough to find, other stupid civilizations messing up the atmosphere. So just as a, another inspiration what life could observe. So getting to the take-home messages. So why you should love life in all caps. So the obvious one is, of course, we need target star catalogs. We have to, define our survey strategy. So similar to, the missions we discussed before. So this community can really help us to build this database of candidate targets, which stars to look at, which stars might be too active, which stars might be binaries or have disks or debris disk or whatever that doesn't make it a good target. So this is really where we need your input. Then your signal is our noise, right? So you might be scientifically interested in stellar variation, whereas for us it's a big noise source. So this is also something we're modeling right now. How does this, if you remember, I told you it's a time series observation. So if our star is varying on the same time scales, it might actually reduce our ability to separate this planetary signal. So this is also something where we could really use help, input from this community. And then something that I'm personally interested in, if somebody is modeling it, I'm really curious to see if we can observe this star-planet interaction in the making, so to speak. So let's say you have a flare, it blows away, or it destroys some part of the atmosphere. For example, like this ozone feature you see here, you have a flare, it destroys the ozone, and then you see the planet replenishing the ozone. So this is like daily observations of Proxima b. So if someone models, these effects of stellar activity on planet atmospheres, reach out to me. We can simulate these observations for life, for example. And then, if you're interested more, so there's actually a huge live conference in Barcelona in about a month, but it's also online. And it doesn't have any registration fees, so there's really no downside to registering. The deadline, though, is next Friday, so you still have a week to register, and maybe just log in a couple of the sessions. But this is really probably a great opportunity for you to even get more up to speed with life, see where your science might fit in, and yeah, that brings me to the end. So in the next decade, or maybe 2 decades, so again, the young generation here will really have the technologies to systematically search for biosignatures in our neighborhood. And life is one of these European-led initiatives, and with my biased view, maybe one of the most promising concepts in this field. And if you want to know more, check out our website, sign up for the newsletter. We have a large YouTube channel, so there's almost all these live papers have at least a 10-minute YouTube video where people explain it, and yeah, become part of this community. Thank you.
Questions?
I actually have a couple, if I can. Can you get back to the sample of stars that you're going to observe? Because I thought it was mostly focused on FGK stars, but I see the majority that you showed there, or maybe it was me understanding.
You mean this?
Yeah, that's more M, right? Because the scale is the same. Oh wait, but the planet yield is not the number of stars that you're going to follow up, right?
Yeah, so for these papers, for this one here, so there's very different scenarios. You can see, for example, here, this is 2-meter diameter, so the rather pessimistic size of the telescope. We have different scenarios, so we can really optimize our observing strategy. So, for example, we can maximize finding terrestrials no matter what host star we get, and then we get something like this. So this paper was about M star planets, so we focused. So in this case, we used I should have said this. We used the optimization to find whatever kind of terrestrial planets. But there are also other observing strategies or survey strategies where we really almost skip the M types and really go for FGK. And then you would obviously get less here and more there. So this was more to illustrate where they are. But these ratios, first of all, you can get make these bars bigger if you just increase your telescope or the throughput. So you can go from 30 to 50. And then depending on how you choose your observing strategy, you can maximize M planets, you can maximize FGK planets. So I wouldn't look too much at the absolute numbers here. So it's a bit of a science level. If it turns out with James Webb there's no atmospheres or M stars, we might skip them completely and focus on FGK. If we find life on TRAPPIST, we might focus on them. So this also makes it a bit scalable or modular for us to do what we want to focus on. Yeah.
Okay. And this, can I ask the second one?
Okay.
I'll be quick. So all of the studies you've done is considering one planet around a single star, dwarf star, right? Does that mean do you have any studies, or you foresee any studies about detection of circumbinary planets or planets around stars that are getting beyond the main sequence?
So if the distance is big enough or small enough, so because this nulling interferometry actually more or less depends on that your host star is a point source, more or less. So even if we get a giant host star too close, it might even be too big to be to use this interferometry. So if you have a wide binary and maybe one of these planets, and if it's far enough out, then we might actually be able to cancel it out. And if they're really tight and actually far enough away to be considered, at least optically, as a point source, then binaries might also be possible, but I would say probably more likely it's going to be that we try to exclude binaries from the beginning, unless we can show. Cool. Yeah. I mean, you can. There's probably going to be geo process where you can convince us, or you can probably also use a live sim to simulate this. So that might be actually a nice project to see how far we could go, or which kind of binaries we should be able to observe. So that might actually be a good test to do now and see if there might be optimizations on the instrument we could do to even make them accessible. Yeah.
Okay, I can.
You almost answered my question already. The baseline of 100 to 600 meters, that's given that the star is just not resolved, right?
Mm-hmm.
Okay.
Yeah. So we can actually, so it's a variable baseline. So we optimize the baseline to have the best transmission in the habitable zone. So this is also where we can just scale our telescope design to be optimized for the habitable zone or whatever else you want to observe. Yeah.
Okay. Thank you. And next talk is by Marika Valentini about exciting opportunities which FORMOST project gives us.
So, hello. First of all, I would like to thank the organizers to give me the opportunity to talk about a project that has taken the last 11 years of my work. So I'm here to talk to you about FORMOST, the 4-meter spectroscopic telescope that will be probably the largest machine for stellar characterizations for the next future. I have a confession as the previous speaker. I don't study exoplanets. My work is focused on galactic archaeology. So if I take your motto, know thy star, know thy galaxy. But we are both interested in better characterizing the stellar content of our galaxies and for better understanding your exoplanets. So for better understanding our galaxy, we need to work in a multidimensional space. So we need to know the position, the distance of our stars, the proper motion to hence calculate their velocities and orbits, plus the multidimensional space where each dimension is a chemical abundance, an abundance of an element, plus one of the most important dimensions and one of the most difficult to measure is the stellar ages. So while Gaia helps us magnificently in deriving our stars' position, distance, and velocities, FORMOST enter in providing the last dimensions, chemical compositions and age, with the help of space missions, in particular for using astroseismology coming from K2, CORO, and the future PLATO mission. Here there is a picture showing the spatial coverage of one of the surveys of FORMOST, one of the galactic surveys. So we aim at characterizing stars in different components of our galaxy, aiming at covering the bulge, the disk, and the halo, and out to the most remote outskirts of our galaxies. You can find a good description of all the surveys, both galactic and extragalactic, in 2 Messenger's special issues that I linked in my presentation. But you just Google Messenger special issues FORMOST and you will find them easily. The instrument then. So the instrument is mounted at the Vista 4-meter class telescopes in Paranal, Chile. The instrument will have has a field of view of 4.2 square degrees, and it will be able to provide spectra for more than 2,400 targets thanks to their fibers. The fibers are feeding 3 spectrographs, 2 low-resolution spectrographs and 1 high-resolution spectrograph. The instrument will be entirely devoted to a survey project for 5 years. And it will be combining not only galactic surveys, but also extragalactic science surveys. And that is the beauty of this project. So we have galactic and extragalactic science sharing the same focal plane at the same moment. And in particular, the code handling these 5 years service code is developed here in Tartu, by the way, so it's a nice connection. Here the instrument, so here there is the focal plane where all the fibers are shown. So we have 2436 fibers. The fiber size is 1.65 arc seconds, square arc seconds, and the minimum distance allowed between fibers is 15 arc seconds. Together with the science fibers, we have other additional fibers, so the calibration fibers that allows a real-time calibration of our spectra, and a series of guiding fibers for adjusting the point of the telescope and checking whether the fibers are pointing in the right place. So, and you see here different colors in the hexagon, that is the field of view of the instrument. Different colors represent different spectrographs. In particular, the red are the high-resolution fibers, while the blue and the yellow are the low-resolution fibers. Here I show you a little movie from last month that show the movie, how the fibers are moving. And you see here two pictures additionally, where you have the reflection of the fibers on the secondary mirror, and the picture below here that shows the focal plane made by the fibers. Yeah, it was the month where where a movie about the something 4 came out, but the Fantastic Four came out, so hence. So they took the. So, and as you can see, fiber position is quite fast. It took 1 minute to position the fibers in their final position, and you can see the fibers red because they are back illuminated in order to measure where the fibers are pointing. Yeah. Go ahead. Okay. So the two spectrographs, here you can have a picture, you can see a schematics of the two spectrographs. On the left, you see the schematics of the low-resolution spectrograph, and on the right, the high-resolution spectra. Both of the spectrographs has 3 arms, a blue, a green, and a red arm in a fixed configuration. As I said before, we have 2 low-resolution spectrographs and 1 high-resolution spectrograph. Here, quickly, I show you what is the spectral coverage and the resolution of the low-resolution spectrograph. We have 3 arms covering that allows a continuous coverage of a spectral range between 3700 angstrom to 9500 angstrom. That is basically the G-band of Gaia. The resolution varies between 4,000 and 7,800. Here there is the same figure, but for the high-resolution spectrograph, that is fed by 812 fibers. The average resolution of the spectra is 18,000, and the spectra here are divided in 3 narrower spectral ranges in blue, red, green, and red. So now the science. What is the science that is being performed by FORMOST? As I said, we are focusing on galactic archaeology, but in synergy with the main space missions like Gaia, PLATO, and we are also making a very complete follow-up of Corot, TESS, and K2 targets. We are in synergy with high-energy skies like Rosita, and we focus on galaxy evolution and cosmology again with in synergy with the Euclid and LSST. Here there is we show the spatial coverage of the survey, here represented by all the targets that we are going to follow up in these 5 years in low resolution and high resolution. The sky coverage of FORMOST will be around 3,600 square degrees, and you can see that we are trying also to go a higher declination in order to have a common fields with large spectroscopic surveys in the northern hemisphere, and to use those fields as calibrators for homogenizing data from all the surveys. That's great. So the science is performed by 18 surveys. And here you can see a list of each one of the surveys. Again, if you want to go into detail about the science that will be done by Foremost, use the special issues of the Messenger ESO journal. Together with these 18 science surveys, there will be 2 additional surveys that will be the calibrators surveys, both galactic, one galactic and one extragalactic, where we will observe pipeline calibrators and training samples for the galactic and extragalactic spectroscopic pipelines. Plus, there will be additional targets provided to just fill the fibers. And maybe you can ask when we can play with the data. So we get data quite soon, because now we are, at the moment, we are performing system verifications, and on the 1st of November, commissioning will start. Then there will be a period where the instrument will be tested whether everything will function as supposed to. So from OB ingestion to observation, and then to the production of the reduced spectra and the spectroscopic parameters. And there will be a period called SPV, the survey program verification that I lead, where we will test whether the strategy designed by survey will be effective in reaching their scientific goals. And then after SPV, the Foremost survey will become operational. Everything that will be observed during SPV, this phase that will start on the last week of February and will last probably between 8 to 10 weeks, everything observed during SPV will be delivered as DR0. And DR0 will happen probably in November 2026, so 9 months after the start of SPV. Then there will be regular data releases, at least 4. As you can see in these schematics, data release 1 will happen probably 2 years and a quarter after the start of the mission. What will be delivered by Foremost? Foremost will provide redshift for AGN and galaxies, radial velocity for stars with a precision better than 1 kilometers per second, stellar parameters with better than 0.15 accuracy index, and for Lurgy, I guess. Abundances up to 15 chemical elements, but then this depends on the resolution of the spectra you want to analyze. And we will provide also the raw and reduced spectra. In particular, for DR0, everything will be provided. So everything that has a spectrum will be provided to the community, while probably the atmospheric parameters and abundances for stars, there will be some limits to them. So we will provide only what converge, and we will focus mainly on temperature, gravity, and overall metallicity. So we go back to galactic archaeology. So Foremost will, as I said before, we provide radial velocity and chemical composition for stars. So this is a schematic showing what we can measure with Foremost, where I showed where are the spectral features in the optic spectrum, and divided every spectral feature belongs to different family of elements, and here I divided alpha elements, iron peak elements, S-process elements, and L-process elements. Below, you can see what is the spectral coverage of Foremost in low resolution and high resolution, together with the spectral coverage, both high resolution and low resolution of WEAVE, that is the multi-object spectrograph located in the Northern Hemisphere in La Palma at the JWST telescope. Go again. So, and you can see here that the two surveys are very complementary, and that's why FORMOST is pushing to have these common fields with the Northern Hemisphere surveys in order to provide a all-sky homogeneous parameters, family of parameters. And we are very, we really would like FORMOST to provide atmospheric parameters and abundances for millions of stars, but we want also these parameters to be the correct one. And here comes all the work that me and my team are doing for the survey program verifications and for the pipeline calibration. So during this SPV time, that will be the content of year 0, we are observing talks about pipeline calibration and training, and we are observing special fields or special targets that are aimed to test the survey strategy. For example, we are observing halo streams to check whether the resolution in radial velocity and chemical abundances will allow scientists to disentangle different stellar populations. We are following up known stars with that are known exoplanet hosts. We are following up seismic targets, cluster, etc. And this is everything that we will have with the data release 0. Plus, we will have all these targets belonging to the pipeline calibration and training. We are sharing those with the major spectroscopic surveys of present and future. So this stripe, the stripe of targets that are above declination 0, FORMOST is sharing all the targets with the WIV SDSS-5, the Milky Way mapper, DAISY, and PFS. I skipped these, I already said. And for these special targets for cross-survey calibration and for internal calibrations, we are trying to cover as much as stellar type as possible. We want to test our pipeline and we want to go beyond the standard FGK calibrators. So we thought about a sample of stars, about 150,000 calibrators divided in 14 classes to cover all the type of stars from OB to white dwarf. And here there is a list of the calibrators we prepared. Again, we have a large amount of binaries, young stellar objects, white dwarf, metal poor stars, clusters, FGK, stars with astroseismology, both giants and both dwarfs, AGB, and down to globular clusters and solar twins. So this is a very complete set of calibrators that FORMOST is observing. And why we need so many? Because surveys are observing that. So this is an example of what is the content of the low-resolution disk and bulge surveys, where this survey is composed by 25 sub-surveys, each one observing different type of stars, spanning from FGK down to planetary nebulae. So we need a calibrator for each type of star, that each type has its own module in our spectroscopic pipeline. Again, here there is the piece of the sky we have in common with all the surveys, and this is a long-going project since many years, and we had different sessions, in particular one in the EAS of last year. And if you are interested in this catalog, please write me, and I will happily provide our cross-survey calibrators in case you are interested in knowing what there is inside. And to link, as a link to the last parameter that we are interested at AGEs, we use seismic red giants for calibrating our AGEs. So red giants with astroseismology are very useful, since astroseismology allows us to measure parameters like gravity with high precision, and therefore refine our atmospheric parameters and abundances. Here you can see in this plot on the top here a comparison between the measurement coming from astroseismology in red and the log G coming from normal spectroscopic analysis, and the log G coming from Gaia. yes, we will follow up the importance, why we focus so much on red giants with astroseismology, because those are our scientific calibrators for age. The astroseismology provides not only a very precise log G, but most importantly provides also mass and radius, and the mass is a very good indicator of age for red giants. And we will use these stars with astroseismology to calibrate then the ages coming from codes like Star Horse or Star Horse Boost that will measure ages for every other stars without using spectroscopic measured stellar parameters and photometry and Gaia parallaxes. Yeah, so this is again the same slide. Here an example of the improvement on age measurements, but I guess you are familiar with astroseismology. Astroseismology helps us to reach a precision of age between 11 to 30%, depending on the quality of the data. And this is something that was really unprecedented before the use of this discipline in measuring stellar ages. So when I started my PhD, for example, I was measuring ages of red clump stars, and I was dealing with errors of from 80% to 100%. So this, for me, it's amazing. It was a really amazing change in the discipline. And here you can see the use of stellar seismic red giants for calibrating the results of Star Horse, for example, the Bayesian code for determining stellar parameters and ages. And you can see here the agreement, or the agreement of non-agreement within mass distances and ages. Another nice use that we can use for red giants is to use red giants with the seismically derived age for calibrating chemical clocks. So we can use the ratios of different chemical elements for deriving an age of our stars. And again, seismic red giants can be one of these calibrators. So, and this is the fil rouge I want to use for this talk, that with Foremost we are providing you, to the community, not only spectroscopically derived atmospheric parameters, but we are doing our best to also provide the important parameters, that is the age. And for doing that, we are following up stars with astroseismology coming from K2, Corot, TESS, and PLATO. And here you can see a spatial coverage of our sample. And again, this is very important. We are tracing different components of our galaxy. We are going quite next to the bulge, but not really, but we are getting there. And we are covering quite well the galactic disk and halo. Regarding PLATO, we are doing a very important follow-up of PLATO targets. The high-resolution disk and bulge survey, called S4, is following up PLATO targets in high resolution from P1 to P4. In their catalogs, they have about almost 200,000 objects coming from PLATO, of course, the field in the southern hemisphere. While the survey where I work, S3, will perform the high-resolution follow-up of a sample of 30,000 red giants selected for better refining the stellar evolutionary tracks. Here you can see the distribution of the 30,000 red giants we selected for PLATO in metallicity and distance, because one of the parameters we need to cover for guaranteeing a better refinement of the stellar evolutionary tracks is metallicity. So we try to reach at least -1 in our sample, -1 dex in metallicity. In conclusion, yes, so Foremost, as I said before, it will be one of the most important machinery for providing atmospheric parameters and abundances for stars. And we will try to better characterize our stars via a very detailed work in checking and validating and hopefully not, but calibrating our pipelines. We are doing also a lot of work in coordinating with other surveys in order to provide you calibrators to put every data coming from different from different spectroscopic survey on the same system of reference. And additionally, we are doing our best for providing you ages, whether they come from seismically refined ages or from tools like StarHorse that we calibrate using astroseismology. And most importantly, I was not allowed to show you some spectra, but you will see spectra in 4 days. So stay tuned. On Tuesday, we will have a big press release about the first light of Foremost. And you can find us in LinkedIn, Blue Sky, and Instagram. And this is a nice picture of Vista, and this shows a bit the path we follow for reaching this. We met some bumps along the road, but we are finally there, and I guarantee you the spectra are looking good, so stay tuned.
Thank you. So, wonderful questions. Yeah, one here.
Thanks, Marika. So I have a question about exposure times. Is it controlled per spectrograph?
No, the exposure time will be always the same. And
for all the 2,000 plus fibers?
Yes. There will be a maximum exposure time of 20 minutes and a minimum exposure time of 1 minute. And the code behind the exposures and the synchronized exposure of every target is very complicated. And you can go to the office of Elmo and ask details, but it is an amazing code, and we manage to reach the completion, the minimum completion parameter for each survey. So each survey will have their targets to perform their science. And yeah,
next
amazing.
question, please. Yes.
Thank you, Marika. We learn a lot from previous surveys, like IESO survey. I have 2 questions for you. Where the data will be saved, because we will have a lot of spectra, right? And
yes.
What are the plans?
Yes, data will be stored at ESO, and they will be provided also. I don't know where did it go, but I show you, there was not anymore. In my presentation, there was a picture, and it is not there. But yes, it's here. This is one of my favorite. No? Okay, there will be at every OB, there will be collected more than 2,400. Yes, here we are. 2,436 spectra. That's indeed a lot of data. If I remember the numbers correctly, there will be about 70 gigabytes per night of data collected. So that's a lot. But yeah, we have storage. Data will be collected in I think it's at IP, and ESO will provide storage as well, plus Heidelberg, if I remember correctly, and CASU. So.
And my second question is about the parameters and abundances. Do you plan to reduce data only once, like with each? What is the strategy?
The strategy is to reduce data with the pipeline, and every time there is a change in the pipeline during planned ticks, let's say, the data will be reanalyzed with the corrected pipeline. So yes, we don't analyze them only once. At every change of the pipeline, there will be a complete reanalysis of the data. And this is an example of what will be on a CCD. So on a CCD, those are on top. You see the 3 arms in high resolution. In the last 2 rows the low resolution spectra, and zoomed in, you can see the spectra are very close together. I think it's 2 pixels separation, 2 to 3 pixels separation between spectra. But yeah, this is, first time I saw this picture, these are not real spectra. This is like they switch on the light in the room. But first time I saw that, I thought, okay, this needs a different way of thinking. This needs a different approach. So not anymore IRAF. So, yes, super Mongo. Yeah.
Yeah.
So,
okay, thank you very much. And the last presentation of this conference, definitely not the last, okay, sorry, I'm a bit messed up. I have a headache, I won't go home, but I am so excited about what Andes can do, because, well, I have not read a lot about it, but
okay.
You will now illuminate us.
Okay, I hope so. I hope it's the last one, so after me it's lunch, so it only goes improving from here on. So today I'm going to talk about ANDES, which is the high-resolution spectrograph for the E-ELT, and I'm going to talk about how ANDES is going to prove the caradal of planets and try to link what is planet formation with what ANDES will do for exoplanets. And of course I do that in my name, but on the name also of a very large consortium team for ANDES, and especially thanks to Katia and Simone and Brunella who helped me with for the stuff with this formation. So you know what the E-ELT is, I think. It's functioning, it has a rotating dome and it will be the largest optical and near-infrared telescope in the world, 39-meter segmented mirror diameter. It will be fully behind adaptive optic systems, it will be on thermal, and it will tackle some of the most pressing issues in astronomy today, from cosmology to solar system planets, and of course, extrasolar planets. And it will see first technical light in 2028. So this is not science fiction anymore. It will be very soon here before we realize. And ANDES and the E-ELT as a telescope will provide 2 fundamental things to us, which is extremely nice angular resolution. You see here comparative images between Hubble, James Webb, and E-ELT, and it will work on the diffraction limited. So it means that in the near infrared, you will have images which are 15 times sharper than what Hubble was delivering a few years ago. And the second thing is the huge unprecedented collecting area, which means you're collecting lots of photons, and this will be really interesting for high-resolution spectrographs in the near infrared that now are mostly operating in 4-meter telescopes, and we will jump to 40-meter class telescopes. And the high-resolution spectroscopy is particularly important because one of the big disadvantages of being on the ground is our own telluric atmosphere. The high resolution will allow us to kind of look through the atmosphere and get rid of it. So obviously a very large telescope comes with a very large suite of complicated instrumentation, which I will completely ignore, although some of them may talk about also exoplanets, and I will focus on ANDES. ANDES, which I already said, is a collaboration of a very large number of institutes putting a lot of effort into it and making it a reality. So what is ANDES? ANDES is a high-resolution spectrograph, which is built in a modular fashion with several spectrographs. The actual design, the requirements go from 0.4 microns to 1.8 microns. I don't know how these points here. But there is the goal to including a K-band spectrograph, which is not yet included in the baseline design. I am personally optimistic about this, but it's not currently part of the ANDES design. And there's also the goal to an extension to bluer wavelength down to 0.35 microns. And it will have different observing modes. I will show it now. And it will have no moving parts because we want the spectrograph to be stable. So in particular, ANDES can observe both in sync-limited and diffraction-limited mode. In the sync-limited, you just put all the light in a fiber or a fiber bundle, and you have 2 fibers, one on the star and one normally that goes into the sky. But also it has an IFU that goes behind an adaptive optic system, and it has a bundle of fibers. And it's quite interesting because don't take these numbers as they are written, because this is being defined, but it will have up to 5 different spaxel size bundles that will have 5 different field of view. It's like a kind of zooming in capability, and it will cover simultaneously the 1 to 1.8 micron region at resolution 100,000, which is really, really nice for spatial for disk and reflected light for exoplanets. So the science priorities are many. This is a high-resolution spectrograph on a 40-meter telescope. You can do lots of science. But the consortium had to build an instrument, and the good news for this community is that it was decided that the top-level requirements will be prioritized depending on science case. And the top science case was exoplanet atmospheres via transmission spectroscopy. It means that we were able to fix the top-level requirements, such as the resolution we needed, the spectral coverage, and several others, so that this science case was the best, had the best specifications. The second one was the valuation of fundamental constants and added new top-level requirements, for example, the extension to the blue. And the third one comes exoplanet atmospheres again, but this time in reflected light. But it already requires, if it does not conflict with top-level requirement 1, then you add new top-level requirements like going behind single conjugate adaptive optics and an IFU. And of course, if you have these requirements, you can not only do science for exoplanets, each of them allows you to do other science cases, including disk formation and so on. Top-level requirement number 4, I think, will not be met at all. So let me start talking about the disk science that Andis will do in particular. Andis will explore the compositional and kinematical properties of disks and explore the scenarios of planet formation. And we saw a nice picture, a very similar picture from Diego 2 days ago or 1 day ago, explaining us how we need to really zoom in into these ALMA images in order to see the processes that are forming. So this picture has seen before, starting from the cloud molecular core collapse down to the formation of exoplanets and the different stages of protoplanetary and planet formation, and how this is a process that occurs fairly rapidly in only a few million years. So I don't need to go through that, but basically in a protoplanetary disk you have lots of interactions, starting with a star, the magnetic field, the gaseous inner disk, and the dusty disk, right? And the evolution of the star and the disk are tightly coupled, because as the gas and disk evolve, with time they are affected by the star and the environment. And what we want to do is we want to zoom in a little bit and see the inner part of these structures, where the inner disk structure contains the winds and jets, the accretion flows and shocks, and close to the star, right? And the structure of the inner disk and its evolution is critical because it will affect the outcome of the planet formation and the planet populations that we see today once they are formed. So this is a very nice cartoon of what you can observe from the optical to the near infrared on a young stellar object. Okay, it looks a bit different in my Mac. But you can see that this is a spectrum of a young stellar object with its shooter, which covers more or less the same spectral range that Andis will cover, but this is at resolution 15,000, Andis will do it at 100,000. And you can probe in the UV, you can study the shock, accretion shocks, with the infrared UV access. You can prove different emission lines all along the optical. You can prove the infrared, the forbidden lines. And if you go further into the infrared, you can see the near infrared excesses, the infrared observing and emission lines, and then also even photospheric features. So Andis will explore all this in the inner 50 AU of the protoplanetary disk and with a higher spectral resolution than we do now. If you want to take an example, this is like shoot a 10 meter. When you take a spectrum of such a star with a 4-meter telescope, it takes you about 2 or 3 minute exposure if you are looking at a transient extrasolar planet, and this will do that in 3 seconds, will give you the same amount of photons. In the inner disk region, Andis will be able to explore the low velocity components because it will probe the kinematics and the kinematics and allow us the separation of the different components in the low velocity in this inner region of the dusty disk, looking at the emission from the photoevaporative wind from that of the gas bound to the disk. And together with the use of IFU, it will be able to apply the techniques of spectroastrometry and resolve the inner regions that are involved in those processes. It will also be able to probe the high velocity component, and it will allow us to test the different jet launching models from the observations of the high velocity component. It will use a large number of spectral lines that will be available in the spectra to probe the different excitation layers of the jets, and it will be able to characterize the jet acceleration and collimation. And also, if we are able to extend to the K-band, now I'm talking now of the K-band, then molecular bands start to appear, and in particular molecular lines of CO, water, or AH that are observed in emission in strong accreretors will give us important clues on the planet formation regions. And if we add to this synergies with METIS, which is another instrument for the E-ELT, which will explore these lower excitation states of these same molecules at longer distances, and ALMA, which is not in this transparency, but also provides longer structures, longer scale structures, this will be highly synergistic to understand disks as a whole. And of course, also, there are molecular winds that you can probe if you go again into the K-band, because this high-resolution spectral imaging of those molecular components will allow us to trace those winds and the role of these winds in protoplanetary disk, the flow of kinematics, and to infer how the angular momentum is lost, and also how planets can also move it, and to test also recent models that have been proposed as wind-driven protoplanetary disk evolution against classical, more viscous disk evolutions. So that's all I have to say about disks. Let's talk about the planets themselves, okay? What is Andes going to do for the planets? What I told you is the most important science case. So Andes is a high-resolution spectrograph, and we will take advantage of the high resolution to see the different Doppler shifts that the planet has if you are on the reference frame of the star. There's a Doppler shift, and along the optics, along the orbit, it's very difficult to go around. Along the orbit, the spectral lines of the planet emitted or reflected lines will shift. And the high resolution allows us to do that, and more importantly, it allows us to also differentiate from the reference frame of the Earth, where the things are stable, zero, and separate molecular absorption features like water or methane that are also in our atmospheres from the telluric absorption. So the exoplanet science case has two different separate cases. The first one is transmission spectroscopy. I think everybody is familiar with that. We've proven that. It's not technologically challenging, and we're just going to do it with a much bigger telescope and much bigger signal to noise. And the second one is a reflected science case, where we see, we get rid of the star and we see the light of the planet being reflected, which has not been yet accomplished. We think it's a matter of signal to noise ratio, and there are some demonstrations ongoing, but it's really at the moment something to be seen if we will be able to do it. Right now, the current level of the current state of the art on exoplanet atmospheres is demonstrated by things like spectrographs like Espresso on the 10-meter VLT, where you can start to see science that differentiates, can do time domain spectra of exoplanet atmospheres, where we can start to see differences between leading and trailing terminators. The James Webb has already been able to do the same thing for giant planets, although it misses the dynamic components because it can see the differences, but it cannot measure the velocities of the winds. And when we move to, I'll start by bigger planets to smaller planets to maintain your attention before lunch. So for giant planet atmospheres, okay, we will be able to see weather and dynamics in a planetary atmosphere in just a single night. Here you have the population of known planets. Every planet which is above the red line, every giant planet, you can see in one transit, you can get anything in the atmosphere. And all the other ones are accessible to Andes. You may need to accumulate 2 or 3 transits. But just to give you an example, this would be a detection of a hot Jupiter. We can only use one spectral order of, this is water, I think, one spectral order of high-res, and we already have detections of the order of 6 sigma. And if we go to the full spectral range that the spectrograph will have, without the K-band, we already talking about signal-to-noise ratio around 50 of elements. And I'm not going to go into more detail, but if you model, you can see the winds on the different terminators and the different speeds, the different heights. It's going to be beautiful if it works. So let's go a little bit to smaller planets. If we talk about small planets, less than 4 Earth radius, and this is a diagram of the known planets a few months or days ago, you can see that the sub-Neptune regime is now being explored by James Webb. This is now the current frontier. This is the smallest planets we can probe for atmospheres now, and we see they have a rich spectrum full of molecular absorptions of methane and water and so on. So James Webb is already providing fabulous data, and this will also be able to check the atmospheres of these planets and provide synergetic observations that will be able to provide the full chemical inventory, at least within the spectral range of Andes, and the velocities in those atmospheres and the winds. But then when you go a little bit smaller, between 2.5, 1.5, then planets start to be very degenerate. The spectra that you can obtain at low resolution can be explained by a diversity of chemical compositions, and we really cannot probe those atmospheres at this moment. Maybe somebody will prove me wrong with James Webb by accumulating several transits, but the planets that we observe and the spectra that we observe can be explained by very different nuclear and atmospheric compositions. And it is here where I think Andes will be able to make a really big contribution, because this is the known population of sub-Neptunes now, planets between 4 and 1.5 Earth radius, and they are all accessible to 5 sigma detection of the chemical composition, not the dynamics, as I explained with hot Jupiters, within one transit. And this is a famous spectra of simulation, of course. We don't have the spectra of K218. We've heard a lot this morning by Giovanna, and you can see that if we put the same chemical composition that James Webb has observed, then we have a detection of over 20 sigma in just one transit observation. And we can fully characterize what's there in the near infrared. So let's go down to small planets. All right, so here's the known population of less than 1.5 Earth radius. And you can see all the planets that are accessible with 5 transits, no more 1 transits. But if you accumulate 5 transits, you can see and characterize the atmospheres of all the planets that are above the red line if they have a CO2-dominated atmosphere. And you can characterize more planets if they have an Earth-like atmosphere. It actually turns out to be easier. So let's do an exercise. We don't have any observation on James Webb of a small planet atmosphere with detections. But if we make the exercise of taking TRAPPIST-1, TRAPPIST-1b in this case, and we put an exact Earth atmosphere in it, which is not maybe the truth, but if we do that, then we can detect the water band with a signal-to-noise ratio of 6 in 2 transits, another water band in 4 transits plus the CO2, and we could detect the oxygen in 25 transits. Okay, so these planets, I should remind you, have a transit duration of 1 hour, so it's not so much time. And if you come to look at this population, this is a simulation of TRAPPIST-1b with OData, the detection of 12 sigma in 10 transits, not 5 transits. But if you come to think of it, I mean, the E-ELT will be very precious time. But 100-night campaign, which seems like a lot, right? But it's only 4 months on a telescope that may last at 40 years. If you do a 100-night campaign, a program, you could explore the best 40 habitable zone planets nearby to us down to the 5 sigma level. So I think that this is really going to be wide opening for understanding whether small planets around M dwarfs have or don't have atmospheres in the first place, and if they have atmospheres, what is there in those atmospheres? And I talked that the exoplanet science case has 2 different cases: the reflection, the transmission spectroscopy, and the reflected light. The reflected light, I think it's a need to try to do this and do it, because the probability of an Earth transit in the sun is only 0.5%, which means that if we have 200 Earth twins around in volume, we can only, by probability, sample 1 of them, right? And the same goes for other spectral type. For M dwarfs, it's a little bit better, but reflected light allow us to probe different things than the transmission spectroscopy that only probes the top layers of the atmosphere. For example, the bottom 8 kilometers of Earth atmosphere cannot be sampled through transmission spectroscopy. They are too opaque. So we can, through reflected spectra, we can probe things down to clouds. We can probe the surfaces if they are available, if they have clear atmospheres, etc. So I have to tell you that this is going to be much more difficult endeavor, all right? But we have identified a golden sample of planets, which we thought would be achievable by Andes. And this is the 5 stars closer to us with 1 Earth radius, or kind of 1 Earth radius, but well, really between 1 and 2, right? 1 Earth radius, which are within the habitable zone of their stars. So they are potentially habitable. Not inhabited, but potentially habitable. And you can see that the amount of nights that Andes would need to dedicate varies a lot. The first one, of course, is proximal ascent, which you can observe on almost 1 night, at least detect the reflected light, and then you want to do molecular mapping, it may take you a couple more nights. And it goes up to 13 nights, okay, depending on the different planets, because they're farther away, the star is fainter, etc. Unfortunately, we lost already 2 of them because the angular separation of the final designs of Andes as they are today may not allow us to go closer than 20 milliarc seconds, around 20 milliarc seconds. So these 2 targets are lost. Good news is one of them was not a real planet. It seems to be star activity. These don't transit, so we are open to that. And we do not expect too many more planets to be on the reach of Andes in the next few years, and this still will take a few years to be functional at the telescope. We expect new discoveries, but we think that the close nearby, unless there's a big survey using a near-infrared spectrograph of the closer and nearby stars, we don't expect many more. But this is not bad news because, oh no, all right, you don't see this. Okay, this is a graphic of all the. This is how long it takes in time from half a night to 50 nights. And this is the angular separation. These are top level is low pessimistic scenario. Middle level is a kind of informed optimistic scenario, right? And there's a gray region here because some are too close to the star. But basically what this shows you is the stars that are here are the ones in the 5, among the 5 golden sample, how long it would take you, right? It's the same thing I put on the table, just in nights. But there is there's a lot of other planets here. So the point of this transparency was to show you that while it's going to be really tricky to do reflected light of a small Earth-like planets in the habitable zone, for sure we'll do maybe a dozen of some Neptunes, and more than that on hot Jupiters that may take less than 1 night to observe in reflected light, and will open very complementary science to that other instruments can do through transmission spectroscopy from space, like James Webb and Ariel. And okay, and this shows you a blob of many hot Jupiters and some Neptunes that would be accessible. You have to imagine it, but I can send it. Okay. Last to final slide, I have talked about disk science. I have talked about finding and characterizing a small Earth-like planet atmospheres, but I completely forgot about other science cases, such as finding Earth analogs via radio velocity. The theme of this conference, Know Thy Star. Imagine, I told you, now how big a signal to noise you will have with a 40-meter telescope where we are integrating a 4-hour transit. The signal to noise of your master spectra for the star would be incredible. We'll do giant planet chemistry and dynamics, and if we have the extension to the CO band, this will be a CO machine, and we will be able to do the Doppler tomographic maps of brown dwarfs now, but also to a small free-floating planets, etc. And if we have the extension to the U-band, we look at the young planet atmospheres, and you can do other things like look at calcium atmospheres through sputtering and so on. Well, it's a lot of things that you can do, really. Start thinking outside of only a small habitable zone exoplanets. So just to finalize, I would like to say that Andes is going to revolutionize our understanding of exoplanets from birth to death, because Andes will explore the inner disk dynamics and the properties of jets and the outflows. It will also measure the accretion properties in young and embedded sources, allow us to make the connections between the inner disk and the outflowing winds. And in synergy with METIS and ALMA, it will connect the outer disk evolution and the larger scale outflows. When you go to already formed more mature planets, it will provide full atmospheric characterization from giant planets, I think, down to the sub-Neptune regime. And it will open also the study of exoplanets in reflected light. And finally say that, and this seems to be now the only instrument in design phase that will be able to measure the chemical composition of habitable zone Earth-like planets, mostly around M dwarfs, if they have an atmosphere. That's something we need to find out. And if they have an atmosphere and if we can measure, we can talk about the last word in my presentation, which is biomarkers. I'm not promising anything, but if they're there, we should be able to search for them. Thank you.
Absolutely fantastic. I really love high resolution spectra. Questions? Yes, here was one.
You briefly mentioned it, but I assume you can easily get the so-called free-floating planets in Sigma Orionis.
Yes.
Right? Yeah.
Yes.
More questions? Seth, yes.
Thank you, Enrique. I'm a bit confused. It's my fault. I hate those correlation plots. When you showed K218b, what do we detect? I mean, it's a molecule, a given molecule, or is the whole atmospheric model? What do we see in this plot?
In this case,
for example, there was also the
this is TRAPPIST,
okay,
K218.
K218.
In this case, well, when you have a plot, this is a cross correlation, which shows you that you have detected a correlation between your data and a model. In this case, the model contains water, hydrogen, helium, and 0.1% of methane. That is the atmosphere that James Webb has detected for that. You could test with different models. You could test with CO2 alone, water alone, a combination. So normally what you do is you use each molecule alone. That's what's called molecular mapping. That's because you cross-correlate the spectra with each of the molecules. And if you have several molecules, then you can do a combined spectra. You generate a model of the atmosphere of the planet with all these features, and it should improve your correlation.
Okay, thank you. And if I may, another quick one. For the reflected light, I mean, it's a different observation mode because of the contrast is 10 to the -7 or -8. So which is this observation mode?
It is the same thing. What happens is that you can first cross-correlate with the template of the star to see if you're detecting reflected light, okay? And then you can also cross-correlate with different model atmospheres that you see. The more complex it is, the model, the more nights of observation you will need to build up signal to noise so you detect all the different molecules that can be on the spectrum. But the technique is the same. You isolate the spectrum, the data, and you do the cross-correlation.
Thank you.
Next, please, yes. Yes.
Okay. Thank you so much for the talk. I'm not an expert at exoplanets, but so recently JWST have just worked on and analyzed some rocky planets, but in most of them, it did not detect any kind of atmosphere in rocky planet, and so. It has been argued that, some argument that maybe JWST is not technically sensitive enough for that. And do you expect that the Andes may have some improvement over those previously observed by JWST and maybe detect some atmosphere on rocky planet?
Yes, James Webb was not really built for small, rocky, Earth-like atmospheres, right? So James Webb is now has conducted several observations on small rocky planets, and it has a large DD program. I'm happy they're doing it because I think that we would like to understand, but it's true that it's going to be very difficult to do through secondary atmospheres. And the problem is the error bars, because you see a flat spectrum and you think, this looks like a flat rock. But within the error bars, many things fit, including an Earth-like atmosphere, a tenuous atmosphere, even a supercritical vapor atmosphere, or even a thin hydrogen atmosphere. Well, maybe many of those are ruled out. But within the error, there's diversity is very large. So I think this is one thing that Andes will be able to do. We will be able to answer if there's an atmosphere there or not, for sure. At least we're talking about hot plats and rocky plats around M doors. For K types, G types, we'll have the big error bars also.
And the last question?
I wonder if this large telescope and super stable, very high resolution, extremely high signal noise ratio instrument, it would be possible to detect those spectral lines from planetary atmospheres without any correlation, just because of the radial velocity changes to the orbital motion of the planet, which is like similar, like it was published in this January, I think, about CRIRES plus observations of transmission spectroscopy, but still.
Yeah, normally, and especially if there are molecules, you need the cross correlation. You're not going to see them in the spectrum. Well, maybe for a large hot Jupiter with a big signal. There are publications where you don't need the cross correlation technique. You just do spectra before and after, and you do transmission. But this works well by individual lines like sodium, potassium, and so on. When you have a molecule with many spectral lines, this gets very complicated.
Thank you.
Thank you again. Unbelievable. Okay, so I ask Alexandra Lechtmetz to come forward to announce the winner of the posters.
Okay, hello. Actually, it's also posters and meme competition, so both of them. Yeah, so we had 10 posters and we had 23 judges. I hope some of them are here, and I thank you all who voted. And we had a very tough competition between 3 poster presenters. And the final winner was decided by us, the volunteers, because they had the same amount of votes for the judges. It was not biased. And the final winner was Nikki. So. She unfortunately had to leave early today, so she already got her prize. So, and next, we also had actually a pretty good memes in our competition. Those two to the left are the last memes that were coming in today. And in the meme competition, the winner was Niti. Is she here? Yes, let's. So yeah, for the winner, we have a notebook for the conference and also the EXOHOST cup. So, congratulations. Okay. And now I want to invite Annaret, our EXOHOST project lead, and also the head of local organizing committee to give the final words.
There was a little mistake. The lead of the local group is Karin Pai, absolute pure gold. Well, I believe that during the conference dinner, I already thanked every one of you, because without you, it won't be such an exciting conference. It was really 3.5 days full of very, very interesting talks and discussions. So I am really grateful to all of you who came and gave talks about your research. But all of this won't be possible without efforts first from Scientific Organizing Committee, who gave an excellent suggestions to invite people for invited talks and to formulate the science scope of this conference. And yes, we have amazing team here. During this conference, I just was able to relax, not think about anything, because all the problems magically found their solution without any interference. So these are you on the photo, and 2 photos also from our excursions. I think I was in the bog, and cranberries were really nice. The cranberry mousse in the end. And I would like to also thank very much our team and invite them here. Please come. As you see, there are so many people who helped with a lot of enthusiasm and devotion, and they were always on time in the right place doing everything necessary. So it was really, really, really good team here. So someone was taking photo. Yes. So come closer. Do we fit to the?
It's better to stand here.
Yes. So this is Karin. This is our pure gold, and you will never have her. Okay. Yeah. Thanks.
With a sweet thank.
Thank you. Okay, lunch.